Okay. So, all right. So, very good evening, all. This is a very fresh morning, very fresh evening today, and we are starting a new course, Power Electronics. Let me introduce myself. I am Professor Rajendra Gharse, MTech from Indian Institute of Science, Bangalore. And in the gate, I was the All India 7th ranker, and I'm your instructor for the course Power Electronics. Right? So, in this session, we are going to discuss about the introduction to the course, and after that we'll be moving towards the first chapter, that is the switching devices. So in the introduction we'll be discussing about what is the definition and the block diagram of the power electronics, applications of the power electronics, advantages, disadvantages of the power electronics, and how to overcome those disadvantages. Okay, weightage, syllabus, and the reference books. Okay, we are going to discuss in the introduction. So during this course, if you are having any doubt, right, you can mail me. My mail ID is it's Rajendra Gharse @gmail.com, or you can WhatsApp me on 7387 864360. Okay, so yeah, so let us first discuss the definition of the power electronics. So friends, as long as the electrical engineering is considered, strictly speaking, it is divided into three areas. Okay, it is divided into three areas. The first area is the power system. First area is the power system. Right. Is my screen visible to all? Is my screen visible to all? Yes. Okay. Yeah. I think some of the students are having the visibility with that issue. Please check your internet connection. Okay. Right. Yeah, this is my email ID and the contact number. Yeah, you can note it. Right. Rudra Prasad, is the video not visible to you? Sir, your video is not coming when going to okay, okay. Pawan, please check once. Pawan Kumar.
Sir,
Yes, please.
sir, voice is not audible.
Voice is not audible.
Somewhat not clear, sir.
Please check the other participants.
Okay, sir.
Now, okay, Rudra is saying now. Okay, 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 okay. Yes, yes, yes. Yeah. Yes, yes. Yeah, most of the students are, yeah, they are saying the visible and okay, no problem. Yeah. Those who are having problem, please check your internet connection once. Okay. My contact details will be available in the class notes. Okay. Right. Yeah. Power electronics definition and the block diagram. So as long as electrical engineering is considered, it is divided into three sub areas. First one is the power system, second one is the control system, and third one is the electronics, right? Power system, control system, and electronics, right? So area power system deals with study of generation, transmission, distribution of electrical power. Okay, means the subjects you might have studied like electrical machines, okay, electrical power systems, switchgear and protection, right? Fault analysis, all those, yes, will be covered under the area power system. Next, second area is the control system. Second area is the control system. The area control system deals with control, that is nothing but the stability of a system. Stability of a system, right? What are the required conditions for the system to be stable? Okay, how to convert that unstable system into a stable system, right? That will be covered under the area control system. And third area is the electronics. Third area is the electronics. The area electronics deals with the study of semiconductor devices. You might have studied the PN junction diode, right? You might have studied the transistor, okay, right? So all these are the covered under the area electronics. And our course power electronics is nothing but control and conversion of large amount of electrical power with the help of electronics, right? Very straightforward purpose. Our course is having the control and conversion of large amount of electrical power with the help of electronics. That is nothing but the power electronics, right? So let me write control and conversion of large amount of electrical power. Large amount of electrical power with the help of electronics, right? With the help of electronics. Very simple purpose. So in this course, whatever we are going to discuss, okay, that will be related to the, yes, controlling of the power, controlling of the electrical power, and the conversion of the electrical power, right? Controlling as well as conversion of the electrical power, right? Next, the block diagram of the power electronics. The block diagram of power electronics. Yes. So in the block diagram, yeah, we're having the blocks like source, next power modulator, next load, and the control unit, So one by one, let us discuss the what is the purpose of these blocks. Okay, so here we're having the source. The source, it may be AC or DC, right? In India, easily available supply is the AC supply, right? So source is AC or DC. Source is a AC or DC, right? Next, the second thing is a load. Right? So for designing a system, right? For designing a system, what purpose we actually design the system? In order to fulfill the requirement of the consumer, yes or no, right? So which type of load is required, that will be decided by the requirement of the consumer, right? For example, suppose, okay, at a particular location, we are interested in designing a particular system, power electronic system, and for that suppose we require a DC motor. We require a DC motor. So here in this case, the load is nothing but the DC motor. Load is nothing but the DC motor. The second thing is, suppose at that location, the easily available supply is the AC. At that location, suppose the easily available supply is the AC. So what I am saying, the available supply is AC, and the suitable motor to drive the load, right, is nothing but your DC motor. So can I directly feed the AC supply to the DC motor? No, right? So in that case, we need to take the help of the power electronic converters, like a AC to DC converter, right? Means that power electronic converter is nothing but it is known as the power modulator. Power modulator. The nature of power modulator depends on the nature of power modulator depends on, yes, the nature, type of the source, and the type of the load, type of the source and the type of the load. Yes. So we are having the three blocks. First one is the source, power modulator, and the load. Okay. The purpose of the power modulator is, yes, to collect the energy from the source, and yes, convert it in such a way that, yes, in such a form that is required by the load, right? Apart from these three, we are having one more block, that is the control unit. What the control unit do? Yes, actually the name itself, it says control unit means what? It will control the power modulator. How it will control the power modulator? So for that, yes, it is taking the help of actual output of the power modulator and the reference input. Here it is a reference input, and here it is the actual output, that is the V0 and I0. These are the actual outputs of the power modulator. So control unit will simply compare the actual output, right? That is the output of the power modulator, and it is comparing with the reference input. And accordingly, it will generate the controlling signal, right? It will generate the, I can say it as a command signal. Now the nature of the command signal, it depends on the type of the modulator. For example, suppose if we are having the rectifier as a modulator, then in that case, the command signal is like your firing angle. Are you getting the point, right? Suppose we are using the inverters. Okay, then we can go for the PWM techniques also, pulse width modulation techniques also, right? Etc. Means the nature of your command signal, it depends on the nature of the power modulator, right? So some of the students joined the late, so I will repeat the definition as well as the block diagram. As I said, as long as the electrical engineering considered, it is divided into three areas. One is the power system, second one is the control system, and third one is the electronics. The power system area deals with the study of generation, transmission, and distribution of electrical power. Control system deals with the study of, yes, stability of a system, and electronics deals with the study of, yes, semiconductor devices, just like your diode, right? BJT, etc. Next, what is the purpose of the power electronics? The power electronics is nothing but control and conversion of large amount of electrical power with the help of electronics. Control and conversion of large amount of electrical power with the help of electronics. That is nothing but the power electronics, right? So we need to only understand, yes, we are interested in controlling the power and at the same time the conversion of the power, right? Controlling and conversion. Conversion means what? Conversion from one form to the another form, just like AC to DC, DC to AC, etc. Right? And control means what? The output voltage. Yes, output voltage we can control. That is, we can vary. That is nothing but the controlling of electrical power. Okay. So simple purpose, control and conversion of large amount of electrical power with the help of electronics. Right? Next block diagram, you can see we are having the four major blocks. One is the source. The source, it may be AC, it may be DC. It depends on at which location we are going to design that power electronic system. Okay. Second one is the load. Second block is the load, right? The type of the load or the nature of the load, it depends on the consumer requirement. Okay, consumer requirement. Next, and the power modulator. Power modulator is like a mediator between the source and the load. Okay, means the power modulator should give the output in such a way that, yes, in such a way, power modulator should give the output, okay, in order to fulfill the demand of the load. And next one, we are having the control unit. Control unit is to control the power modulator output. Okay, to control the power modulator output, right? So this is the simple block diagram of the power electronics, right? Next, let us discuss the applications of the power electronics. So friends, power electronics is a very vast area, and in electrical engineering, it finds applications in all the areas, just like your speed control of electrical machines, power system, transportation area, domestic area, renewable sector, right? It finds the, I don't know why some of the students are raising their hand.
Sir,
Yes, yes, please.
Please.
sir, I'm not any doubt, sir, but a small thing is that, sir, you are writing in that note, na, sir. It's very small.
Yeah.
It's very length is very small, na, sir. Only 3 or 4 lines are visible, and the remaining thing is not. Like in previous, they are using that another note, sir. In that we can see whole thing like that. Here we can see only few things, na, sir.
Okay, okay, okay. Just a minute. Now please check, is it visible?
Yeah. Sir, a bit more, sir. I mean,
Means actually I am reducing the percentage here.
yeah, yeah.
Please check, is it fine?
Sir, do it 30, sir. Let's
Yeah.
some more, sir. Some more. Zoom out. Yeah, yeah, fine.
Is it okay?
Yes, sir, fine. Thank you, sir.
Okay, okay, okay.
Because we are unable to connect the previous and the next thing. Thank you, sir.
ठीक है, ठीक है, ठीक है. Okay, okay, okay. Please check where is it visible? I have made it 35% only.
Yeah, now it's visible, sir.
But the students who are using the mobile, right, they are having the problem. So small. That is the issue. Okay. Okay, let it keep it as 40%. Please check once.
Sir, only 5 lines are visible, sir.
Yeah, no issue.
Okay, sir. No problem.
Please check now, those who are using the mobile. Now it is okay. Okay, 40% is correct. Okay, okay. At the starting, yeah, definitely these issues will come. Yeah, black background is that feature is not available here. Black background. Okay. I tried to for that black background, but it is not available in this note. Yeah, I will check with that sketchbook. Okay. Yeah. Okay. Sir, increase the size to now. That is the issue. Some students will say, okay, some will ask for 50%. Yeah. So let me keep it as 45. Okay. Yes. Okay. Next, applications of the power electronics. Okay. So as I said, power electronics finds the number of applications in almost all the areas. So let us discuss first applications in speed control of electric motor. First is the speed control of electric motor. Or it is also known as drive, right? Drive. Okay. So in the drive, we are having DC motor drive, and second one is a AC motor drive. Vijay Reddy, do you have any problem? DC motor drive and AC motor drive. Okay, so this is a special area actually, electrical drive means, right? So where you can find the applications of the power electronics, right? Applications of power electronics. Next, second one is the power system. Second area is the power system. In the power system, you can find the HVDC transmission. What we are doing in HVDC transmission? Yes, let me explain it in short. We are generating the AC power, okay, with the help of transformer. We are stepping it up, okay, and here we are putting the rectifier, right? Here it is a rectifier that will convert the input AC to the output DC. We are transmitting it over a long distance, right? And again, at the receiving end, we'll be having the inverter. Next, again, it is a step down, okay, with the help of transformers. And again, it is given to the load, okay? So between these 2 points, whatever the system we are having, that is your HVDC, okay, HVDC transmission. So we are having the blocks like converters like rectifier and inverter, okay? These are, yes, from power electronics, okay? These are the power electronics converters, okay? So HVDC transmission. Next, it finds in the power system, again, we are having the active power compensation. Active power compensation, reactive power compensation, reactive power compensation, active filters, active filters. These are the some of the applications of power electronics which you can find in the power system area, okay, power system area. Next, the next one is the transportation. In the transportation, yes, we are having the let us consider first, that is the rail. Rail means your electric traction system. Electric traction system. So in the electric traction system, yes, we are having the line supply, right? The line supply which is available is single phase 25 kilovolt, okay, 50 hertz. This is the supply we are having. This supply is available, okay, for the traction system. And which motor we are using? Generally, the DC series motor is preferred. Why? Because DC series motor is having the high starting torque. Yes or no, right? So generally the DC series motor is preferred. So now you can check available supply is, we are having this single phase AC, okay, and your here the motor is a DC motor. So can we directly connect that AC supply to the DC motor? No. So in that case, we need to go for the converters, right? Means we need to use the rectifier here, okay, AC to DC converter, right? So this is the one application. Or you can check in the Japan in the 1960s, right, when they were thinking about the bullet train. At that time they experimented for the induction motor also. Okay, induction motor is also used in the traction system because of the invention of the power electronics technology only, right? Because in the power electronics we are having the inverter. What the inverter is doing? Inverter is, yes, it is converting the fixed AC to the variable AC. Variable AC means what? Inverter is the circuitry which is giving the output in terms of variable voltage and variable frequency. Okay, so variable voltage and variable frequency means the inverter is the circuitry which can give the output in terms of variable voltage as well as variable frequency. So in the case of induction motor, in your electrical machine subject, you might have studied the V by F ratio control method we are having. Okay, what is that V by F ratio control? Yes, we are varying the voltage and the frequency in the same proportion such that V by F ratio is maintained constant. Yes or no, right? So with the help of inverters, we can, yes, use the induction motors also for the traction system. Okay, next, coming towards the next one, after the rail in the transportation, we are having the road transportation. Road transportation. In the road transportation, yeah, if you check the AC systems in the buses, in the cars, okay, these requires actually the low voltage DC supply. Okay, that is nothing but your UPS, and UPS is the application of the power electronics only. Okay, UPS is the application of power electronics only, right? Third one, we are having the air transportation, right? Air transportation, that is in aeroplanes. In the aeroplanes, we are having the lighting system, AC system. Next, pilot cabin control panel. Pilot cabin control panel. For all these, yes, we require a low voltage DC supply. Okay, so here the UPS is preferred. Okay, and as I said, UPS is the example of or the application of power electronics only, right? So it finds the applications in the transportation area. Next, after the transportation, power electronics can find the applications in, let me put here, four, in the renewable sector also. Renewable area, that is the solar, right? So if you check the solar panels, yeah. So if you check the solar panels gives the output in terms of the DC. Okay, so can I directly feed the output of the solar panel to our grid system? No, na, right? So for that case, we need to take the help of power electronic converters. Okay, means here we need to use the inverter circuitry. Okay, and after that inverter, once inverter converts that DC to AC, after that we can feed into the grid system. Okay, apart from that, in the road system, we are having the today's very hot field, that is the electric vehicles. Okay, if you are a student of third year or the final year, you can think about the electric vehicles, say projects, small projects on the electric vehicles. Okay, because this is the area where a lot of research is going on nowadays. Okay, and most of the countries, okay, have already accepted that in order to minimize the global, in order to minimize the global warming. Okay, yes, we need to reduce the emission of the gases, right? That is the CO2 gases. So for that, they have accepted to go for the electric vehicles. So definitely till 2040, probably you can find all the automobile sector, okay, that will be covered by the electrical engineers only, right? That is the electric vehicles only. Okay, so for the electrical engineers in the coming days, this is a where you can find a lot of the opportunities in this specific area, electric vehicles. Let me put here EVs, that is the electric vehicles, right? Next, apart from that, it finds the applications in the domestic also area. domestic area. Where we are using, you can check the fan regulator. Previously, we were using the fan regulator. Yes, that is nothing but the speed control of single phase induction motor, right? Fan regulator means what we are doing? We are controlling the speed of the single phase induction motor. But in the traditional way or in the conventional way, if you check, there we were using the, yes, external resistors in series with the motor. Okay, and we were varying those external resistors, and with the variation of those external resistors, yes, what happens? The voltage drop across those resistors will be it was changing, and due to that the voltage across the motor was changing. Okay, so you can check this fan regulator. Yes, here yeah, the first one is the conventional way, that is the conventional fan regulator. Okay, and the second one is the power electronics based fan regulator. So you can check here 1 2 3 4 5, these are your, yes, this is the knob. Okay, and 1 2 3 4 5, these are the points. Okay, so when this knob is at point 1, when this knob or this pointer is connected to the point 1, it is like, yes, all the resistors, right, all the resistors will be in series with the motor, and here we are having the supply is 220 volt. Okay, so you can check here, this total potential difference is 220 volt. When this high resistance will be connected in series with the motor, okay, definitely it is like a resistor in series with the motor we are having. So definitely the current will be flowing into the circuit, and according to the Ohm's law, when current flows through the circuit, yes, when current flows through the resistor, it will cause the potential difference, that is nothing but the voltage drop. Okay, so supply voltage minus some drop across these external resistors will cause, okay, supply voltage minus this drop is nothing but the voltage that will be available across the motor. Means ultimately what we were doing, yes, we were changing the voltage across the motor, okay, with the help of these external resistors. But what is the drawback of this method? The drawback of this method is due to these external resistors, yes, it was causing the extra losses, power loss in these external resistors. So as the power loss is taking place, definitely the system efficiency decreases. Okay, so this is the actual drawback of this conventional system method. Okay, but whereas you can check here in the power electronics converters, same motor we're having, that is the fan, means the single phase induction motor. The available supply is a AC supply 220 volt. Available supply is 220 volt AC supply. Next, here we are using the TRIAC, right? We are using the TRIAC. Definitely in the coming sessions, you will understand what is the TRIAC. Okay, TRIAC is actually the bidirectional switch. Okay, and we are using the DIAC also. The purpose of the DIAC in this circuit is the DIAC provides the triggering pulses to the TRIAC. Okay, so here we are having the single phase AC supply. So supply will be like this. It is equal to Vm into sine of omega t. So the supply will be like this. This type of supply will be getting 0 to pi, pi to 2 pi, and 2 pi to 3 pi. This is the supply voltage Vs. Okay. Now, yes, this TRIAC is the controlled switch. Right? So it is like, when, as I said, the TRIAC is a bidirectional switch. Okay, it is a controlled switch. So when between 0 to pi, okay, when we are going to apply the gate signal to the TRIAC, right? Suppose at this instant I am applying the gate signal to the TRIAC. So what will happen? Let me consider this instant is theta. Okay, so after theta, our TRIAC will turn on. So across the motor will be getting the wave shape like this. This is theta. Definitely at pi plus theta also I need to apply the gate pulse. This is only short introduction I am giving. Definitely in AC to AC voltage controller, okay, that particular chapter we are going to discuss this circuitry again. Okay, so we'll be getting the output voltage like this. This type of output voltage, it is from theta to pi, pi plus theta to 2 pi, and here it is 2 pi plus theta to 3 pi. Okay, so you can check here, it is a sudden change we are having, right? Vs is actually purely sinusoidal, supply voltage is purely sinusoidal, but now with the help of TRIAC, right, means at this instant when trike is turned on, yes, what will happen? Current will flow into this loop. Current will flow into this loop. Okay. So this will act as a short circuit. This will act as a short circuit. Ideally speaking or theoretically speaking, it will act as a short circuit. But practically, our switches are having some voltage drop. Okay. Why that voltage drop takes place and those things we are going to discuss. Okay. In the coming sessions. Right. So when it is in the on state, yes, what will happen? The supply voltage minus a very small drop, across this trike. Okay. So remaining voltage will appear across the motor. So that's why here this voltage that is appearing across the motor will be nearly equal to that of your supply voltage. That is after from theta to pi I am saying. But whereas in this case, what was happening? In this case, it was like some voltage drop was taking place. Okay. And if you check the power loss in the external resistors, yes, Bhanu Prakash. Yeah. It is simply a no need to write the notes. Actually, I will provide you the lecture notes. Okay. Yeah, Bhanu Prakash. Actually, it is only introduction part, right? So that's why I am taking it fast. Okay. Yeah. Theory means this full, whatever I will be writing here, that full you will be getting. Okay, in the PDF form. Okay. If you are having any doubt, we'll be having a after the session. Okay, you can ask the doubts because it is very difficult for me currently. Almost 550 students are attending, and it is very difficult to answer all the questions, right? Yeah. I will give you notes tonight only. Don't worry about the notes, right? Yeah. Okay. Right. So here it was causing the high power loss. So due to that, the efficiency of the system was decreasing. But whereas if you check, yes, in the power electronics based fan regulator, okay, comparatively the power losses in a power electronic switches is a very small. Okay, is a very small, because you can check power electronics switches we are having, these switches actually causes a very small voltage drop across it during the on state. It is hardly in the range of 0.7 volt, 1 volt, 1.5 volt, right? It is like this. Okay. So that's why after this, when we start the first chapter, switching devices, at that time you will understand what is the power losses, right? And why those power losses are very less. Okay. And power losses in our power electronic switches are very small. That is the bigger advantage of the power electronics technology. Okay. So here efficiency will be high. Here the efficiency will be high in this case. Here you can check the output voltage we are getting. Definitely it is not a pure sinusoidal. Output we are getting. But you can check here whether it is a AC or DC. It is a AC only because it is having positive values, negative values, positive values, and again next the negative value will be there, right? So we'll be getting the fixed AC to the variable AC converter. Okay. Yes. In detail, we will discuss that AC voltage controller part later on. Next. So in the domestic applications, we are having the fan regulator. In the computers, power electronics technology is used. Okay. So now you can check here the power electronics technology finds applications in electric motor speed control, right? And these applications comes under the medium power. Okay, medium power application. Medium power. Next, power system based applications. These are comes under the category high power applications. High power applications. Transportation, it is again in the medium power applications. Next, domestic. Okay, domestic, it comes under the low power applications. So you can check here. Power electronics finds applications in almost all the areas, that is the high power, medium power, and the low power, right? High power, medium power, and the low power areas, right? Yeah. So this is about the applications of the power electronics. Next, let us discuss the advantages and disadvantages of power electronics. Is this visible, or shall I increase some percentage here? Let's check once. Yeah, I think it is okay, na? Right? 60%. Okay. So advantages and disadvantages of power electronics. So let us first discuss the advantages. After that, we will discuss the disadvantages, and next will be how to overcome these disadvantages, right? So advantages, as I said, the power electronic switches are having a very less power loss. So due to that, our power electronic converters are having very high efficiency. Okay, power electronic converters are having a very high efficiency, because in the converters, what we are doing, in the converters we are using the switches only. Okay, and as the switches are having the less power losses, therefore our converters are also having the high efficiency. Okay, so we can check increase the efficiency of power converters due to less loss in power semiconductor devices. This is the very big advantage we can see. The second one, the life period of power converter circuit is long compared, if you compare with the electromechanical converter, the life period of the power electronic converter will be very high, right? It will be more. Less maintenance is required. Why the maintenance required is less in the power electronic converters? Because the rotating part is absent here, right? Rotating part is absent due to the absence of the moving part, okay, moving components. So here it requires a less maintenance. The dynamic response means what? Dynamic response means, suppose we are having the power electronic converter, and that power electronic converter is feeding to load, okay, and if the load changes suddenly, then how our converter responds to the change in the load, that is nothing but your dynamic response. That is nothing but the dynamic response. So definitely power electronic converters are having, yes, the dynamic response very fast compared to that of electromechanical converters. Next, the size and weight of power electronics converters is less, hence the installation cost is also less, right? Less installation cost. So these are some of the advantages of the power electronic converters, or you can say the power electronics system. Disadvantages. The bigger disadvantage of the power electronic converters is it generates the harmonic in the supply system as well as in the load. Okay, why it generates the harmonics? Because in the power electronic converters we are having the switches, and switches, what we are doing, the switches we are turning on, turning off, turning on, turning off. Due to that, what is happening? Yes, due to that, it causes the generation of harmonics into the supply system as well as in the load system also. Okay, definitely we are going to discuss how to find the harmonics and those things. In the mathematics, we are having the very famous tool, that is the Fourier series. Okay, the Fourier series analysis, the basic purpose is it compares the periodic non-sinusoidal signal with the sinusoidal signal, and it finds which harmonics are present, okay, into that non-sinusoidal periodic signal, right? So we are going to discuss about the Fourier series and how to find the harmonic contents also, right? Next, the AC to DC and AC to AC converters operate at low power factor under certain conditions. Yes, due to this harmonic generation, right? Due to this harmonics, okay, introduction, our AC to DC, that is the rectifiers, and AC to AC, that is the inverter, okay, converters operate at a low power factor under certain conditions. We'll discuss which are those conditions and those things. Okay, next, the overload capacity. This is important. The overload capacity of power electronic converters is low if you compare the electromechanical converter and the power electronic converter. the overload capacity in the case of electromechanical converter will be definitely more compared to that of your power electronic converters, right? Means I cannot put a load which is greater than that of the rated capacity of our converter. Okay, so overload capacity is very less here. The cost of power electronic converters is high. Definitely the cost is high. So these are the disadvantages. How to overcome these disadvantages? So for that, we need to go for the advanced and efficient fast switching, high frequency switches. That is the fast switching devices. Next, we can use the filters, advanced converter, just like a resonant converters, forward converters, etc. And the advanced control techniques, that is the PWM, sinusoidal pulse width model. PWM means pulse width modulation, sinusoidal pulse width modulation, space vector modulation, direct torque control. Space vector modulation and direct torque control, these are not there, okay, in India at the UG level. But if you go for the PG, okay, MTech, right, MTech level or integrated PhD level, you can find the these 2 points definitely in the syllabus, okay, of the power electronics. Okay, so PWM is there in our syllabus. Sinusoidal PWM is also there. Multiple pulse width modulation, multiple PWM is also there in our syllabus, right? So these are this is about the discussion about how to overcome the disadvantages. Okay, next, coming towards the main point, that is the syllabus. Okay, syllabus. So if you check the syllabus of GATE and ESE carefully, yes, I have highlighted some in the ESE syllabus. I have highlighted some points, okay, with the red color. These points are extra for the ESE. Okay, means for ESE students, the GATE syllabus is there, plus they have to study these extra points also. Okay, so let us first discuss about the GATE syllabus. The static VI characteristics and firing gating circuits for thyristor. Static VI characteristic, definitely they have only mentioned the static VI characteristic, but we need to cover the static VI characteristic, dynamic also, okay, gate characteristic also, etc. Everything we are going to cover, right? Because as long as the GATE syllabus is considered, they only give one line, okay, but it is not like that. They will ask the question only related to the static VI characteristics. No, it is not like that. Okay, so firing and gating circuit, this is the added one. This topic, firing and gating circuit, it was not there in the GATE 2020 syllabus, but in the GATE 2021 syllabus they have added, and this point is also there for the GATE 2022 syllabus. Okay, so firing or gating circuits. Next, that is the UJT based firing circuits. Okay, MOSFET, metal oxide semiconductor field effect transistor. Here the MOSFET means power MOSFET. Okay, as long as the power electronics is considered, we are going to deal with the power devices only, not the conventional devices, not the traditional devices. Okay, signal level devices, whatever you have discussed in your EDC subject, okay, electronic devices circuits or analog electronic subject, okay, or digital electronic subject, those were the conventional, that is nothing but signal level devices. But whereas in power electronics, we are having the power level devices, we are having the power level devices. So that's why here MOSFET means the power MOSFET only. Next, IGBT, insulated gate bipolar transistor. Okay, they have mentioned only 1, 2, and 3 switches. They have not mentioned the diodes, okay, TRIAC and GTOs here in the GATE syllabus. But as these are the basic building blocks, okay, we need to discuss these switches also under the GATE syllabus, right? So we are going to discuss diode also, TRIAC also, and GTO also for the GATE as well as ESE students, right? Next, DC to DC converters, DC to DC converters. That is nothing but the choppers. Okay, in that we are having the step up chopper, step down chopper, step up, step down chopper. Okay, 3 circuits major we are having. Okay, and in order to, what is the drawback of that chopper circuit, and so that we are going to modify it, we are going to add one inductor, we are going to add one capacitor, and after that it is named as a buck boost and buck boost converters. Okay, buck boost and buck boost, these are the advanced converters actually. Choppers are your basic circuits. Okay, choppers are the basic circuits. So at the while discussing the chopper circuit, while discussing the DC to DC converters, we'll discuss what is the difference between the chopper, basic chopper circuit, and your buck boost and buck boost converters. Okay, next, single and three phase configuration of uncontrolled rectifiers. Yes, specifically I would like to highlight this point here. Uncontrolled rectifiers they have added. Single phase and three phase configuration means diode rectifiers. Diode rectifiers for single phase as well as three phase. Okay, for single phase as well as three phase. Okay, we are going to discuss. Previously it was not there in the GATE 2020 syllabus, but in 2021 they have added it specially. Okay, next, voltage and current commutated thyristor based converters, right? Voltage commutated and current commutated thyristor based converters. Next, bidirectional AC to DC voltage source converters. Okay, AC to DC voltage source converters. Next, magnitude and phase of line current harmonics for uncontrolled and thyristor based converters. Yes, here magnitude and phase of line current harmonics. Okay, means whatever I addressed that Fourier series analysis, right? That we need to take the help of that Fourier series analysis. Okay, Fourier series in order to identify the harmonic contents in the output voltage. Okay, so that is nothing but here line current harmonics and its effect, its magnitude, okay, and its phase. Also, we'll discuss how to remove those harmonics also, right? Next, power factor and distortion factor. Actually, these are related with the AC to power factor and distortion factor. For AC to DC converters also there, right? As well as for inverters also there, right? Next, single phase and three phase voltage and current source inverters. Single phase and three phase VSI and CSI. Sinusoidal pulse width modulation. They have mentioned only sinusoidal pulse width modulation, but we are going to discuss the multiple pulse width modulation as well as single pulse width modulation, because unless and until you study the single pulse modulation, you will not understand the sinusoidal pulse modulation, right? So this is the syllabus for the GATE. They have not mentioned the diode, triac, GTO, but we need to discuss it. Okay, we need to, because these are the basic. Without diode, you cannot study the thyristor, because diode is a 2-layer and single junction device, na? And thyristor is your 4-layer and 3-junction device, right? Yeah. Yes. Next, for ESC, yes, if you check the syllabus, the added points only I will discuss. The first one is the diode, power diode. It is not mentioned in the GATE syllabus, but definitely we are going to discuss in the GATE as well as ESC. Triac and GTO, these are also we are going to discuss for GATE as well as ESC students. Next, basic concepts of adjustable speed AC and DC drives. So fundamental of electrical drives, that is AC drives and DC drives. This is a specially added topic for the ESC only. For GATE students, the drive chapter is not there, but for ESC, yes, the drive chapter is there. Okay, so that's why I have given the name as, they have given the name as power electronics and drives, but whereas for GATE, it is only power electronics, right? Next, resonant converters. Yes, some advanced converters they have added in the ESC syllabus, that is the resonant converters. Forward converter is also there. Next, high frequency inductors and transformers and power supplies. Okay, high frequency inductors and transformers and the power supplies, right? That is the pulse transformer, and we will discuss what is the difference between your conventional, that is power system, whatever the transformers we are using in the power system, those are the utility transformers, right? Utility system transformers. But whereas the transformers like a pulse transformer, which we are using in the power electronics, okay, it is a high frequency transformer. So what is the difference between the two? Which material is generally preferred for the pulse transformer, right? Those things we are going to discuss. Okay, so now one announcement is there. As this is the GATE plus ESC common batch, okay, so in these sessions, actually, we are going to discuss the common syllabus only. Okay, and for ESC students, the additional topics and the conventional unsolved questions, okay, that will be discussed later on. Okay, in the ESC mains batch, so specifically in the ESC additional topic batch, not the mains batch, ESC additional topic batch, right? So next, weightage. Yeah, this course is having the I can say the high weightage for the GATE, ESE as well as PSUs. Okay, PSUs means state level, GENCO, TRANSCO and DISCOM, right? So if you check for the GATE, there will be around 1 to 2 questions of 1 mark each. So total weightage of 1 to 2 questions means it is a 1 to 2 marks. Next, 4 to 5 questions of 2 marks each. So total weightage is around 8 to 10 marks. So if you add this, the weightage for the GATE is around 9 to 12 marks. So it is a roughly 10% weightage is there, right? Out of the 100 marks, right? Out of the 100 marks. This is the weightage for the GATE. Next, ESE. Next is the ESE. In the ESE, we are having the level 1 and level 2. In the level 1, that is the prelims exam. That is the objective type questions will be there. So around 10 to 12 questions will be there. 2 marks each. So weightage will be around 20 to 24 marks. And for the level 2, that is the conventional, that is the mains. Okay, there will be around 6 to 8 questions. 6 to 8 questions of 10 marks, or some questions will be of 16 marks or 20 marks. Okay, so weightage is around 75 to 85 marks, right? So very high weightage. And apart from these examinations, if you check for the interviews, okay, if you go for the MTech in Power Electronics, okay, they will ask the recent technology based questions, right? So next, PSUs, that is GENCO, TRANSCO and DISCOMs. PSUs, that is GENCO, TRANSCO and DISCOMs. Yes, the roughly weightage is around 8 to 12 marks out of the 100. Okay, 8 to 12 marks out of the 100, right? So if you check for all the 3 examinations, the roughly weightage is around 10%. Okay, 10 to 12% weightage is there, right? So this is about the weightage. Next, let us discuss the reference books. Reference books. Yeah, I will suggest the 3 reference books. First one is the Power Electronics by Dr. P.S. Bimra, right? Second one is the Power Electronics by M.H. Rashid, and third one is the Power Electronics by Mohan and Robbins. Okay, you can refer any of the book. Okay, this is actually over and above, but I will suggest that if you refer the class notes, this is also sufficient. But if anyone want more to study, then you can refer these books. Okay, apart from these books, we are having ACE publication books also. So it is a electrical engineering study material with classroom practice questions. That is the volume 1 book. You might have got this book. Okay, and in these sessions, actually we are going to discuss the numericals. Okay, related numericals which are there in this volume 1 book, right? Next, we are having the ESE 2021 booklet, right? That is the previous examination solved papers are there, right? And next one is the GATE 2021. Okay, previous GATE solutions is there. Okay, so these 3 books, I suggest that you refer these 3 books. Okay, and definitely the questions which are there in this book, in this volume number 1, we are going to discuss it while discussing the concept. But I suggest that apart from these questions, because only these questions are not sufficient. Okay, so it will be better if you refer the previous ESE and the previous GATE question papers for minimum of 10 years. Okay, minimum of 10 years, right? If you are preparing for GATE, then also I will suggest that please refer the question papers of ESE. Okay, question papers of ESE. And for the ESE students, I suggest that please refer the question papers of CSE, right? That is the Central Service Examinations. Okay, CSE. Because CSE is somewhat higher level. After that ES, and after that GATE we are having, right? Yeah. Now, yes, one more point. This syllabus, whatever they have given, okay, and at our end, actually, I have divided this syllabus. I have divided this syllabus into the various chapters. Like first chapter is the switching devices. Switching devices. In this chapter, we are going to discuss the different switching devices, their characteristics, their operations. Okay, starting from the power diode, after that the thyristor, right? After that, the GTO, DIAC, TRIAC, IGBT, etc. Right? Second one, AC to DC converters. AC to DC converters. Yes, in these uncontrolled converters, controlled converters, single phase, three phase. In the single phase, again half wave, full wave for various loads like a resistive load, RL load, L load, C load, RE load, RLE load, etc. Right? We are going to discuss. Third one, DC to DC converters. DC to DC converters, right? That is the choppers or some recent one, that is the buck boost and buck boost converters. Okay. Fourth one is the inverters, that is the DC to AC converters. DC to AC converters, right? DC to AC converters. Next, that is the inverters. In this, we are going to discuss single phase half bridge inverter, full bridge inverter, three phase 120 degree, 180 degree mode. How to control the voltage, that is the single pulse, multiple pulse, sinusoidal pulse width modulation technique. How to remove the harmonics, right? And current source inverter. Okay. Fifth chapter is AC voltage controllers. AC voltage controllers, right? Yes, total it will take around 17 days, okay, to complete the syllabus, right? AC voltage controllers, or it is also known as AC voltage regulators also. AC voltage regulators or AC voltage controllers means input is a fixed AC, output is a variable AC. Okay, so, and the sixth one, that is the fundamentals of drives. Fundamentals of drives, right? Okay, so these are the topics, right? This full syllabus I have divided into these 6 topics, right? So as long as, yeah, let me reduce it now, right? So as long as these 6 topics are considered, yes, the weightage, if you check comparatively, chapter number 1, chapter number 2, chapter number 3, and chapter number 4, these 4 chapters are having a very high weightage, right? In the GATE as well as ESC examinations, and also at your PSU level also, right? Comparatively here, chapter number 5 is having somewhat lesser weightage. Okay, and chapter number 6 is also having a somewhat lesser weightage. Okay, chapter number 6 is only for ESC, only for ESE. And also in the DC to DC converters, there are some added topics in the for the ESC students, right? In the ESC syllabus, just like a resonant converter, forward converter, etc. Right? We'll discuss it later on, right? So this is actually these 6 topics we are going to discuss. Okay, so let us first start with first chapter, switching devices. Switching devices, right? So this is about the yes, discussion about, yeah, discussion about the introduction to the course power electronics. Next, let us start the first chapter, switching devices. In this chapter, we are going to discuss the switch. What is the switch? Which are the different types of the switches? That is the ideal switch, practical switch. What is the difference between the ideal switch, practical switch, right? After that, we'll be discussing about the power diode, thyristor in detail, because as long as your syllabus is considered, we are having the detailed analysis of the thyristor. But whereas for other switches, just like your power diode, or you can check the DIAC, TRIAC, GTO, etc., we are having only the introductory part. Okay, that is the operation and characteristic, right? Like this. So let us start first, signal level and power level devices. Signal level and power level devices. So signal level devices and power level devices, the difference is signal level and power level devices. What is the difference between the two? signal level devices are the devices which are having the current rating, which are having the first of all the voltage rating of the range plus minus 10 volt to plus minus 15 volt, right? Hardly voltage and voltage rating is around plus minus 10 volt to plus minus 15 volt. This is for signal level devices. And whereas the power level devices are having the voltage rating of few volts to kilovolt, few volts to kilovolt, right? So for power level devices, the voltage rating varies from volt to the kilovolt, right? Volt to the kilovolt. This is the difference between the signal level, power level. For the signal level devices, the current rating is varies from few microampere, okay, few microampere to the few amperes, right? So microampere to ampere only, till ampere only, right? Next, for the power level devices, if you check the current rating, it is from ampere to kiloampere, ampere to kiloampere. Third one, for signal level devices, the power rating is from milliwatt to few watts, milliwatt to few watts. But whereas the power level devices are having the power rating, okay, from watt to megawatt, This is the major difference between the signal level devices and power level devices. Signal level devices means what? The devices which you have studied during the subjects like EDC, electronic devices and circuits, right? Or analog electronics or digital electronics, right? All these devices were the signal level devices. But whereas
Hello, sir.
yes, Anil, do you want to?
Hello, sir. Voice is major.
Voice is?
Hello, sir.
Yes, please.
Hello, sir. Am I audible, sir?
Yeah, you are audible.
Sir, your voice is not getting.
Okay. What about the others? Please check your internet connection once. Very clear voice, sir. Very clear. It's okay. Yeah. Please check your internet connection once. Anil.
Hello, sir. Voice not audible.
No, I think but for other students it is okay, they are saying. Please check once, right? You are saying it's breaking. Okay. Okay. Yeah. Yes, this EDC means electronic devices and circuits. So in your university, the might be the name for that subject. Okay, it might be the analog electronics, right? Basic circuit, somewhat like electronic circuit theory, etc. Right? So that is the EDC. AE means analog electronics. DE means digital electronics. Right? Power level. For the power level, we are having the subject that is the power electronics. So in a power electronics, we are going to deal with the power level devices, not with the signal level devices, right? So now my question is, for example, suppose we are having a diode. In the signal level also, you have studied the diode. In the power level also, we are having the diode. The only thing is, in the signal level, we had a PN junction diode. Definitely here also, in the power level also, we are having the PN junction diode only, right? But the thing is, here the name is the power diode, and in that case the name was only PN junction diode. The difference is, you can check the same diode we are having, right? PN junction only in both the cases. Here the voltage level is hardly few volts, but whereas here the voltage level is it is changing from volt to the kilovolt. It varying from volt to the kilovolt, right? So how to increase This particularly as long as the semiconductor devices are considered, the voltage level of the device or the voltage rating of the device, it indicates the voltage blocking capacity. Please try to understand, this statement is very important. For a semiconductor devices, the voltage level is nothing but, or the voltage rating is nothing but the voltage blocking capacity of that particular device. I am saying voltage blocking capacity of that device. Okay, voltage blocking means what? When the device is in a off state. Okay, when the device is in a off state, at that time maximum how much voltage that device can block is nothing but the voltage rating of that device, is nothing but the voltage rating of that device. Please try to understand, this statement is very, very important. What I said, yes, the voltage rating of a device, it indicates the maximum voltage that can be blocked by that device when it is in a blocking mode, when it is in a off state. Okay, so now my question is, here the blocking voltage capacity is hardly few volts, but here the blocking voltage capacity of kilovolt till kilovolt. So what we are going, or what we are doing into the construction of the device, so that our device, yes, is able to block, the device is able to withstand with that high voltage, or device is able to block that high voltage. So for that, actually what we are doing, we are, yes, let me write here, we are adding, yes, we are adding or inserting, let me write, we are inserting lightly doped layer in device cross section. We are inserting lightly doped layer in a device cross section, right? Means lightly doped layer, actually there is one relation in the semiconductor physics, that is the device physics. Okay, the voltage blocking capacity of the device is inversely proportional to, yes, doping density, inversely proportional to doping density. So let us understand first what is the doping density. You might have heard, in the doping percentage, we are having the highly doped, that is the heavily doped, after that the moderately doped, after that the lightly doped. Yes or no, right? Heavily doped or highly doped, the meaning is we are adding large number of impurities. Yes or no, we are adding large number of impurities, okay, into the device. So if you check, if the device is heavily doped, then it is like we are adding the large number of impurities into the device structure. Then what about the doping density? What do you mean by the density? Density is nothing but, yes, number of doping density means is nothing but number of charges which we have doped divided by the volume of the device, right? So can I say that for the heavily doped device, yes, for the heavily doped or the heavy doping, can I say that the doping density is high? For moderately doped, the doping density is somewhat lesser, and for lightly doped, the doping density is, yes, very less. Are you getting the point, right? So please try to understand, the voltage blocking capacity of the device is inversely proportional to the doping density. This conclusion we have taken from the device physics, means if we add or if we insert the lightly doped layer into the device cross section, then what will happen? Yes, means what? Lightly doped means what? Doping density is less, right? So if the doping density is less, so it is like a voltage blocking capacity will be more. Yes or no? So let me write, doping density is less for lightly doped material, right? Lightly doped material or lightly doped device, you can see, right? So if we add a lightly doped layer into the device cross section, then it will definitely help in increasing the voltage blocking capacity of the device. So that's why, yes, generally we add a lightly doped layer, right? And one more important thing, the voltage blocking capacity also depends on the width of that lightly doped layer, that we will discuss. Okay, so this is the one thing, how to increase the voltage blocking capacity of the device. So for that we need to, yes, add the lightly doped layer into the device cross section. This is the one thing. Second thing, if you check the differences, yes, voltage is over. Current, in the current also we are having, here the current range is microampere to ampere, right? Few amperes or the several amperes we are having. But here if you check the current, in the current rating in the power level devices, it is changing from ampere to the kiloampere. So how to increase the current carrying capacity of the device? Yes, simply increase its cross section area. You might have studied in the electrical machines. Okay, suppose I am using one conductor, right, for the transformer winding. If I want to increase the current, right, then if I want to increase the current rating of the transformer, what we are supposed to do? We need to select the conductor which is having a more cross section area. Yes or no, right? So here current carrying capacity can be increased with a more cross sectional area. So let me write cross sectional area is more, means current carrying capacity is more, right? Cross sectional area is more means current carrying capacity is more, right? This is the difference actually. Okay, so now here you can check signal level. In the signal level, current carrying capacity is less, means definitely cross sectional area is less, and at the same time, yes, doping density will be more, right? Because voltage blocking capacity in the signal level is less, right? So that's why the here the lightly doped layer is not required in the signal level device, but in the power level we need to add the lightly doped layer. When we discuss the power diode, at that time you will understand, okay, how we insert that lightly doped layer into the device structure. So you can check here. Here I have shown the two devices, right? That is the outer that is a picture of the devices. One is, this is a signal diode, and second one is a power diode. One is a signal diode and second one is a power diode, right? So signal diode, you can check here, comparatively the device length is small, the device cross sectional area is also small. But whereas you can check in a power diode, yes, here the cross section area is also more, right? And here the device length is also more, you can check. Is this clear? So this is a power diode, this is a signal diode, how it looks, right? So why the cross section area is more? Because the current rating is more. And why the how the voltage blocking capacity we have increased the voltage blocking capacity by adding or by inserting the lightly doped layer. So this is actually the difference between signal level devices and power level devices, right? Next, moving towards the next point, switch. Let us discuss the concept of switch. Okay, the switch is represented, yes, like this. Switch is a bistable device. It is a switch. Let me write it as a yes. This is a switch. Because the switches we are going to use in order to form the power electronic converters, right? So switch. It is a bistable device. It is a bistable device. Right? So it is a bistable device. So it is having the two states, steady states we can say, right? One is a on state and second one is a off state. one is the on state and second one is the off state, right? So it is having the two states. One is the on state and second one is the off state, right? So on state of the switch, on state of the switch, it is represented like this. This indicates the switch is in the on state, or switch is going to be in the on state, right? Arrow is like this, na? So terminals are A, B, right? This is the pole and this is the throw, right? Pole and the throw, right? So if the arrow is in this direction, so it is, the meaning is switch is going to be in the on state, right? Switch is going to be in the on state. And second one is the off state. Second one is the off state. Off state, right? So arrow will be like this. Okay, arrow will be like this. Again, A, B, this is the pole and this is the throw. Pole and the throw, right? Arrow indicates the switch is, yes, opening. That is, switch is going into the off state, going into the off state. On state means what? It is like a closed switch. Off state means what? It is like a open switch. Okay, it is like a open switch, right? Now the switch is a bistable device. It is having the two states. One is the on state, second one is the off state, right? On state and the off state. Now, strictly speaking, the switches are having the two types. One is the ideal switch, second one is the practical switch. So first of all, let us discuss about the ideal switch, and after that we will discuss about the practical switch, right? First of all, ideal switch, and next one is the practical switch. So let me put the heading, ideal switch, ideal switch. Ideal switch, right? So let me write on state. First state is a on state. Ideal switch during the on state, right? So this is the A and B. So during the on state, let me draw the circuit here, one where we are using the ideal switch, right? Where we are using the ideal switch. So suppose this is the voltage source V. Here I am using the ideal switch. Suppose this is currently in the on state, and we are using a resistor here as a load. Yes, this is your switch. Consider the voltage across the switch is VSW. Current flowing through the switch is ISW. Okay, VSW and ISW, right? So on state, we have considered this switch is an ideal switch. This switch is a ideal switch, right? So always keep it in mind. When the ideal switch is in a on state, when the ideal switch is in a on state, it causes a zero voltage drop. It causes a zero voltage drop across it. Okay, I am saying ideal switch is causing a zero voltage drop means what? It is behaving as a perfect short circuit. It is behaving as a perfect short circuit, right? So let me write ideal switch in the on state. It is acting as a perfect short circuit. Ideal switch in on state behaves as perfect short circuit. Perfect short circuit, right? It will behave as a perfect short circuit, right? Next, so if it behaves as a perfect short circuit, what about the voltage across the switch? Recall from network theory. If we are having a perfect short circuit, what is the voltage across that perfect short circuit branch? It is a 0 volt, right? So therefore we can write voltage across ideal switches when it is in on state, it is a 0 volt, right? So voltage across ideal switch during on state. Let me write it as VSW dash on. VSW dash on means what? It is a on state voltage across the switch. It is equal to 0 volt. Very, very important, right? The ideal switch voltage during the on state is a 0 volt. Now, ideal switch voltage is 0 volt. So what about the current in the circuit? Can I say that current in the circuit is nothing but the ISW only, right? And if you apply KVL, you will be getting V by R, but we are not interested. Means here, how much current is flowing into the circuit? How much current is flowing through the switch? Yes, it is a non-zero current, right? It is a non-zero current. So let me write here. Yes, current flowing through the switch. Current through switch during on state. During on state, we are discussing about the ideal switch, right? So during on state, yes, it is minus infinity to ISW to plus infinity, right? Now you might be thinking that in this circuit, how the negative current will be flowing? No, this is a general statement. This is the general statement I have made, right? Because the current in the circuit depends on the circuit parameters, na? Whatever the current flowing into the circuit, it depends on the circuit parameters. That is, what is the voltage, what is the resistor, and those things, right? So suppose if the voltage is sinusoidal, then we'll be having the current is positive, negative, like this, right? If the voltage is negative, then we'll be having the negative current, right? So that's why this is the generalized statement, minus infinity to plus infinity, minus infinity to plus infinity. Means in the ideal switch during the on state, the voltage across switch is 0. Current flowing through the switch is non-zero. Current flowing through the switch is non-zero. So now, what is the power loss in the ideal switch? What is the power loss in the ideal switch during the on state? Yes. Power loss in ideal switch during on state. Power loss in ideal switch during on state, right? During on state. Yes, during on state, what is the power loss? We know power loss P is equal to voltage across switch into current flowing through the switch. So it is a VSW into ISW. But what is a VSW during on state? It is a 0 and ISW is non-zero, right? So it is a 0 into ISW. So if you take this product, it is equal to 0 watts. So ideal switch, yes, power loss during the on state is equal to 0 watt. It is equal to 0 watt, right? Next, what about during the off state? Let us discuss for the off state. Second is the off state. Ideal switch during the off state, right? So switch is open. Switch is open now, right? Switch is open. A, B. This is a pole, and here it is a throw, right? Pole and throw. So ideal switch during off state. So equivalently, we can draw the circuit like switch is open, na? Same circuit. Let me draw. This is a R. This voltage is V. This is a switch. Voltage across switch, consider it as a VSW. Current flowing through the switch, it is a ISW, right? So switch is open. So during the off state, ideal switch behaves as a perfect open circuit. During the off state, ideal switch behaves as perfect open circuit. Perfect open circuit, right? So it is a perfect open circuit during the off state. So what is the current in the open circuit? It is a 0 ampere, right? So therefore, can I write switch current during the off state is equal to 0 ampere, is equal to 0 ampere. And what about the voltage across the switch? Voltage across the switch is open, na? So voltage across switch, it depends on circuit parameters. It will be non-zero voltage. It will be a non-zero voltage. So let me write here, during off state, yes. during off state, voltage across switch, voltage across switch. Yes, it is a VSW. Let me write it as a off. Okay, it will be from minus infinity to plus infinity. This is again a generalized statement I am saying. If if for the given circuit, definitely it will be positive. It will be non-zero and positive. But in the generalized way, we can say that it may be positive, it may be negative, right? It depends on the how we have connected the source and those things, how we have connected the switch also, right? It depends on this. So during off state, the voltage is non-zero, current is zero. So can we find the power loss during the off state? Power loss in a switch during off state. Power loss in ideal switch during off state. During off state. Yes, during off state power loss, we know power loss P is equal to VSW during off state into ISW during off state. So therefore, what is P? P is equal to VSW during off state. It is a non-zero, right? So let me write it as a VSW off. And what is the ISW? It is a zero now. So therefore, what is power loss? It is a 0 watt. So always keep it in mind. Ideal switch during on state as well as off state doesn't cause any power loss. Okay, any power loss. So let me write. Yeah. Yes. Ideal switch during on and off state. On and off state doesn't cause any power loss, right? Any power loss, right? So therefore power loss is 0 watt. Next, apart from these two stable states, we are having one transition state also. We are having one transition state also. So let me put the heading transition state. We are discussing about the ideal switch only, right? So transition state, let me write it as a transition state. Yes. Transition state means what? It is a transition from on state to the off state and off state to the on state. Okay, means suppose initially the switch is in a on state, and when the switch is turning off, means whatever the transition is there now from on state to the off state, that is your transition state. Similarly, that is nothing but your turn off transition actually. Similarly, we are having a turn on transition also. We are having a turn on transition also. So let me write transition state. One is the turn on transition, turn on transition, and turn off transition. Turn on transition, and second one is a turn off transition. Turn off transition, right? So turn on transition means what? Yes, it is a on to off transition. Okay, turn on transition means it is a off to on transition. Okay, so T off to T on. Off to on transition, that is nothing but your turn on transition, right? So it is a off to on. Means switch is in a off state, switch is in a off state, right? But it is switching into the on state, right? It is switching into the on state. That is nothing but your turn on transition, right? So off to on switching, off to on switching. Let me write. Okay. And next one is the turn off transition. Turn off transition means switch is in a on state, switch is in a on state, and now it is switching into the off state. Okay, so on to off, on to off, on to off switching. They have asked the question. Okay, I think if you check the GATE 2016 question paper, they will give you the voltage and current waveforms, right? And they will ask what is the transition and also find the power loss during the transition period. Okay, so in that case, you need to understand on to off transition means it is a off transition. Off to on transition means it is a on transition, right? So off to on means it is a on. Here it is off to on means it is a turn on transition. And on to off means it is a turn off transition. It is a turn off transition. So now let me draw the voltage and current waveforms for the turn on and the turn off transition for ideal switch. Okay, for ideal switch. So let me first indicate the turn on transition, and next we'll discuss the turn off transition. So here, turn on transition. Suppose for a switch, yes, at this instant we are applying the controlling signal, right? This is a control signal. Next, voltage across the switch and current flowing through the switch. Okay. Just try to understand this. Okay. So, is it visible? We're going to draw the waveform only. Yes. All your questions will be answered at the end of the session. Okay. Right. So, yes. Okay. Now, so now here I have drawn the, I have taken the three plots. First one is for the control signal, means at this instant, I am going to apply the controlling signal to the ideal switch, and so that our ideal switch will turn on, right? Next, this V indicates the voltage across the switch at the instant of turn on transition, because at this instant I said ki ideal switch is turning on, means before this, what is the state of the ideal switch? The ideal switch will be in the off state. Yes or no? At this instant, the ideal switch is turning on. The meaning is before this, the ideal switch will be in the off state now, and at this instant it will turn on, right? Means after this it will be in the on state. Before this it will be in the off state. So now we are going to draw the waveform for the voltage across the switch. When switch was in the off state, and also when the switch will be in the on state. Similarly, we are going to draw the waveform for the current flowing through the switch when the switch will be in the off state and when the switch will be in the on state. Okay, so from that you will understand during the turn on transition, what will be the time and what will be the power losses in the case of ideal switch, right? So now, yeah, please listen. At this instant, actually the switch is turning on. So before this, the switch will be in the off state. Switch will be in the off state in the ideal switch, we're discussing. When the switch is in an off state, what is the voltage across the switch? Whether it is a zero or non-zero. When ideal switch is in an off state, what is the voltage across the switch? Whether it will be zero or non-zero. Yes, definitely it will be a non-zero voltage. Non-zero, right? Off state I am saying. Okay, so it is a non-zero. So non-zero voltage means, let us consider the voltage across the switch during the off state. Definitely it will be a non-zero voltage, means this much voltage consider. This is the voltage across the switch when switch is in an off state. At this instant, the switch is turning on. Okay, so therefore the voltage across the switch will suddenly decrease to the zero. Voltage across the switch will be suddenly decreasing to the zero. Similarly, you can check the current. How is the current waveform? So here switch is in an off state, Here switch is in a on state. Okay, here switch is in a on state. So when switch is in a off state, what is the current flowing through the switch? It is a zero. Ideal switch we are discussing. So ideal switch during the off state, it behaves as a perfect open circuit. So therefore current flowing through the switch will be zero only, right? So here current flowing through the switch should be zero during off state, and as soon as switch turns on, the current will become non-zero. Current will become non-zero. This current is a I ampere. So at the before this instant, it is a off state, and here we are having the on state. Here we are having the on state. So now point to be noted, this characteristic is valid for ideal switch only. For practical switch, what is the change? Definitely we are going to discuss. Okay, so for ideal switch, if you check, before this instant the switch was in off state, after this instant the switch is in on state. So can we say that this line indicates, yes, the transition period of the ideal switch? So you can check here, as soon as the controlling signal is applied, ideal switch turns off, turns on immediately. So once ideal switch turns on means current suddenly reduces to the zero. Within a zero time, the voltage across the switch has decreased to the zero value. Within a zero time, the current flowing through the ideal switch has increased to the non-zero value, right? Means this indicates, you can check, this indicates this is a transition state or turn on transition. This indicates the turn on transition. This is a turn on transition. Turn on transition, right? What about this? This is also turn on transition. This is turn on transition. So definitely we are discussing the turn on transition. So therefore this is also turn on transition. So always keep it in mind, as this is the ideal switch. Okay, so turn on transition time in the case of ideal switch is equal to zero. Is equal to zero. Means within a zero time, the ideal switch can turn on from off state to the on state, from off state to the on state. Okay, so let me write, turn on transition time is equal to how much? It is a 0 ampere. It is a 0 second. It is a 0 second. Similarly, can we draw the waveform for the turn off transition? How is the turn off transition? For the turn off transition means what? Yes, let me draw one more plot here. This is a control signal. Voltage and a current. Right. So here we're having a control signal. At this instant, control signal is removed. Means before this switch was in a on state. After this switch will be in the off state. Okay, after this switch will be in the off state. Okay, so when switch was in a on state, what about the voltage across the switch? Ideal switch, it will be zero. So ideal switch voltage will be zero when it is in a on state. As soon as, yes, it is removed, the ideal switch will turn off. So turn off means the voltage will become non-zero. Voltage will become non-zero. Similarly here, for the current, that current waveform, if you check, when switch is in a on state, switch is in a on state, so this is a on, this is a off. When switch is in a on state, what is the current flowing through the switch? It is a non-zero. So current is a non-zero. And next, when switch is in an off state, the current becomes suddenly zero. So this current is a I, this current is 0 ampere, right? So this is a transition instant. So this is a on here, this is a off here, on here and off here. So here please understand, at this instant the switch is turning off. Okay, so that's why can we say that this indicates the turn off transition. Turn off transition. Turn off transition means on to off switching. Turn on transition means off to on switching. Okay, so it is a on to off, so that's why it is a turn off transition. And what is the time corresponding to the turn off transition? It is a zero, na? Yes, within a zero time, the switch voltage is changing from zero to the non-zero value. Within a zero time, the switch current is changing from non-zero to the zero value. So that's why the turn off time and the turn on time in the case of ideal switch is always zero, right? So let me write here. Yes, turn on time, turn on transition time, not the turn on time, turn on transition time. Turn on transition time is equal to 0. Also turn off transition time is also equal to 0. So what about the power loss during the transition? So therefore power loss, yes, during transition period, is equal to power loss during turn on transition plus power loss during turn off transition, right? So let me write power loss during turn on transition. Yes, zero power, good. So power loss during, yes, turn on transition, right? And power loss during turn off transition. Plus, there should be the plus, not the multiplication. Let me write here plus. This is a power loss during turn off transition, right? So here, what is the power loss during turn on transition? If you check the turn on transition, yes, this is our turn on transition. Na? Voltage is decreasing in a zero time, current is increasing in zero time. So if you take the product of voltage and current, it will be zero, right? You can check at this instant, it is a voltage non-zero, current zero. And next in a zero time, it is changing. Na? So that's why the power loss will be zero in the turn on, as well as you can check in the turn off also, the power loss will be zero, right? So it is a 0 plus 0. So it is equal to 0 watt, right? So power loss in an ideal switch during a turn on transition plus turn off transition is a 0. Ideal switch power loss during the on state is a 0. Ideal switch power loss during the off state, it is a 0. Is this clear? Right? So this is a power loss during transition period. This is the ideal switch actually, but in practical switch, this will not, this is not 0. Okay, why it is not 0, we'll discuss. Okay, next one is the external circuit requirement for ideal switch. In the case of ideal switch, external circuit requirement. So external circuit requirement means what? In order to turn on the switch and in order to turn off the switch, in order to turn on the switch, generally we require a triggering circuit, or you can say the gate drive circuit or the base drive circuit. Okay, but in the case of ideal switch, it doesn't require any triggering circuit. Also, it doesn't require any turn off, any external circuit to turn off. Okay, means it doesn't require any commutation circuit also. I'm using the word triggering circuit and the commutation circuit. Triggering circuit is required to turn on the switch. Commutation circuit is required to turn off the switch. Okay, but in ideal switch, the external circuit, okay, for turning on as well as turning off is not required. Okay, is not required because it is ideal switch, right? So ideal switch doesn't require, yes, triggering, doesn't require triggering circuit to turn on and commutation circuit to turn off, right? But whether the ideal things exist in real life, no, na. Whether the ideal things exist in real life, no. Ideal things means what? Are the ideal device or the ideal transformer you might have studied, ideal switch we are studying, right? So ideal meaning is, the meaning is, as long as the research point of view, if we are constructing or if we are designing any device, our motto, our target should be that, yes, at the end, we should, yes, we should reach near to that the ideal switch. That is our target actually. But whether in practical case, is it possible to achieve the characteristic same as that of the ideal switch? No, we cannot achieve the characteristic same as that of the ideal switch for the practical case, because we are having some limitations in the practical case. Because for the manufacturing or for the construction of the device, we are using some material, na? That material is having the resistivity non-zero. Due to that, our ideal switch will be having the property like it will be having the non-zero resistance during the on state, and due to that non-zero resistance, it will cause some voltage drop during the on state and power loss also. Okay, we'll discuss. Means in the practical case, the ideal things does not exist actually, but ideal things are just like for setting the target, okay. Yes, our task is to reach near to the ideal thing, right? So ideal switch doesn't require, here should be the switch, doesn't require triggering circuit to turn on and commutation circuit to turn off. Okay, so this is about the external circuit requirement. Next, let me add one more point, that is the thermal stability for ideal switch only. Okay, thermal stability or thermal constraint. Thermal stability or thermal constraint. Okay, so the voltage, this is the current, right? Voltage means voltage across the switch, current means current flowing through the switch, right? So thermal stability, the word thermal indicates the temperature, the word thermal indicates the temperature. Okay, so always keep it in mind. As long as semiconductor devices are considered, okay, due to the power loss in the devices, it will cause the heat generation, and due to that heat, the temperature of the device increases. So that's why in the practical cases, in the practical switches, okay, we are having one concept like a safer operating area, okay, and that safer operating area will be given, okay, based on this thermal stability or the thermal constraint. Okay, thermal stability and the thermal constraint. But if you check in the case of ideal switch, yes, when switch is in an on state, right, what is the voltage across the switch? We have written now, when switch is in an on state, the voltage across switch will be any voltage between minus infinity to plus infinity. Yes or no? So any voltage between minus infinity to plus infinity, right? Next, when switch is in an on state, I am saying you can check any point on this VSW, corresponding to this point. What is the y coordinate? Any point on this VSW axis, what is the y coordinate? Y coordinate is nothing but ISW. Yeah, ISW will be 0 na? So ISW 0, any point on the VSW axis, the value of ISW is 0. The meaning is current flowing to the switch is 0. The meaning is switch is in an off state. So if I indicate the point here, the meaning is the switch is in an off state. Okay, switch is in an off state, right? Any point on the VSW axis means our ideal switch, yes, can withstand with the minus infinity to the plus infinity voltage. This is what we have written in the on state. Next, any point on the ISW axis, any point on the ISW axis. What about the VSW value? any point on the ISW axis, what is the VSW value? VSW value is 0. VSW 0 means what? Voltage across switch is 0. Voltage across switch is 0 means what? Switch is in a on state. Yes or no? So you can check. When switch is in a on state, what is the current flowing through the switch we have written? It is a minus infinity to plus infinity. So that's why it is a minus infinity to the plus infinity. It is a plus infinity here. This is a minus infinity, right? Minus infinity to plus infinity means. And what about the power losses in the ideal switch? For all the three states, you can check. We're having the on state, we're having the off state, we're having the transition state. In all the three states, what is the power loss? Power loss is 0. So as the ideal switch doesn't causes any power loss. So what about the heat generation? Heat generation will be 0 now. Power loss is 0. So that's why heat generation will be 0. Heat generation is 0. So that's why the increase in the temperature of the device, it will be 0. So that's why whether ideal switch will be having any thermal constraint? No. Ideal switch will not be having any thermal constraint because yes, it is having the 0 power losses. So due to that, heat generation will be 0. Due to that, temperature will be 0. Rise in temperature will be 0, right? So therefore, you can say yes, whatever the entire VI plane is there, this entire VI plane will be the safer operating area for the ideal switch. I am writing this entire plane is a SOA, that is a safer operating area. But this is only for the understanding purpose because we know ideal things does not exist in a real life. Okay, so for ideal switch, yes, entire VI plane is safer operating area. Safer operating area. That is a SOA. Means ideal switch can operate at any point on this VI plane. At any point on the VI plane means what? Plus infinity to minus infinity voltage, plus infinity to minus infinity current, right? And it is not having any thermal constraint also because power loss is 0. Because the power loss is 0, right? So this is about the ideal switch. But we know ideal things does not exist in real life, right? Those are only for the understanding purpose. Those are only for the study purpose. So after that, next we are going to discuss the practical switch. Okay, practical switch, right? So I think it's 7. We'll take a break here. We'll start at 7:15. Okay, 7:15. 15 minutes break is there. We'll start at 7:15. Class will be continued till 9 p.m. Okay, take a break of 15 minutes, right? Okay. So now let us discuss about the practical switch, right? Practical switch. It is also bistable device. Two stable states are on state and off state, and next one is the transition state, right? So total 3 states we are going to discuss: on state, off state, and transition state, right? So let us write here on state first. On state, same A, B, this is a pole, and here it is a throw, right? This indicates the switch is in a on state, right? Switch is in a on state. Now, so when switch is in a on state, the difference between ideal switch and the practical switch is, during on state, the ideal switch behaves as a perfect short circuit, but whereas the practical switch, okay, it will cause some voltage drop. It will cause some voltage drop across it, okay, due to its properties, due to its properties. So let me write here. This is a R, this is the voltage V, this is the switch we are having. Voltage across switch is VSW. Current flowing through the switch is ISW. This is a VSW. This is a ISW. Okay. So as I said, the practical switch during the on state, definitely it will behave as an on circuit. It will behave as a closed switch only, but it causes some voltage drop across it. But it causes some voltage drop across it. Right. So let me write practical switch during on state causes some voltage drop. Voltage drop. The range of the voltage drop is around 0.7 volt to 1.5 volt, or at max of 2 volt. Okay. It varies from device to device. So 1.7 volt to 1.5 volt. Okay. So in the practical switch, you can check for the silicon diode also. Whatever you might have studied in your second year analog electronics subject. When silicon diode is in a on state, it causes a voltage drop of 0.7 volt. Na? We generally say, right? So that is nothing but the on state voltage drop of that switch. On state voltage drop of that switch. Okay. So always keep it in mind. Ideal switches doesn't causes any voltage drop. It acts as a perfect short circuit. But whereas due to the property of the practical switch, okay, these switches causes some voltage drop across its terminals. Okay, so that's why VSW during the on state is a non-zero. Definitely its value is very small. It is hardly 0.7 to 1.5 volt. Okay, but it is a non-zero. But it is a non-zero. So let me write VSW. VSW during the on state is a non-zero. It is a non-zero voltage, right? And what about the current? As it is acting as a closed switch, so definitely current will be non-zero, right? Definitely the current will be non-zero. In general way, I can write current through practical switch during on state. Yes. How much current? It is a minus. Let me write it as I double dash less than or equal to ISW. That is the switch current, right? ISW less than or equal to plus I dash. Okay. So it varies from minus I double dash to plus I dash. Okay. Any value minus I double dash will be any value. Okay. It is not like that minus infinity to plus infinity. In the ideal case, it was a minus infinity to plus infinity. But in practical case, it is a minus I double dash to the like a plus I double dash, right? Minus I double dash to the plus I double, because it is having some finite value. It is having some limit. Why the limit is there? Due to the, yes, thermal stability constraint. Due to the thermal stability constraint. We'll discuss it while discussing the fifth point, that is the thermal stability or the thermal constraint. Okay, next. This is the current and the voltage during the on state, okay, for the practical switch. Next, during the off state, the second state is the off state. Off state. Yes. A, B, yes, pole and throw is there, and arrow should be like this. Okay, so switch is going to be, yes, off. This is the voltage source. Suppose this is a resistor. So voltage across the switch is VSW. Let me write it as a VSW. And here it is a ISW. ISW, right? So here, yes, this voltage is V and here it is R. So practical switch during the off state, okay, it causes some leakage current through it. If you check the ideal switch during off state, it was behaving as a perfect open circuit. So that's why current flowing through the ideal switch during the off state, it was a 0 ampere. But whereas in a practical switch, this current will be like a leakage current. That is a very small current. That is a very small current. You can check in the diode also, you might have studied. Okay. So when diode is in a reverse bias mode, okay, that is in the off state. So the current that was flowing through the diode, it was a, yes, reverse leakage current. Na? Similarly, if the voltage across the diode is less than the 0.7 volt, diode is in a forward bias mode. And if the voltage across the diode is less than the 0.7 volt, okay, then what will happen? Diode will be like in an off state only, and it allows a very small current. That is nothing but the leakage current. Ideally speaking, our practical switches should not allow the current when they are in an off state. But due to the practical difficulties, due to the properties of the practical switches, okay, a very small current flows through those switches. Okay, very small current will be flowing, and that small current is nothing but your leakage current. That is nothing but the leakage current. Generally, it is in the range of microampere. Generally, it is in the range of microampere, right? So let me write. Yes. Practical switch during off state. During off state, yes, allows very small current through it, right? That very small current is leakage current. That very small current is a leakage current, right? So very small current is a leakage current, right? So now here we can write what is the value of, yes, current is a very small, that is a leakage current. But what about the voltage across the switch? What is the voltage across the switch here? Switch is in an off state, very small current is flowing here. Okay, so what is the voltage across switch? The voltage across switch, it may be positive or it may be negative. It depends on circuit conditions. It depends on circuit parameters. Okay, so VSW, let me write. During off state, voltage across practical switch, okay, is non-zero, and it is a from minus V double dash less than or equal to VSW less than or equal to V dash. Okay, V dash. So it is now finite value, but whereas in the ideal case, if you check, it was a minus infinity to the plus infinity, but now here it is a finite value. Now it is a finite value here, right? So the current was finite when it was in a on state, right? And voltage here also, it is a finite. Okay, so let me write here, ISW is a non-zero right? ISW is a non-zero. Now, yes. So what are the power loss here? Power loss in practical switch. Power loss in practical switch. So first let us find during the on state, and next one is the during the off state, right? So first during on state, during on state. So now whether this power loss will be zero or non-zero? Yes, power loss in the practical switch during the on state, whether it will be a zero or non-zero? VSW into ISW. Yes, during the on state, yes. Yeah. Non-zero, right? Non-zero, good. So it is a non-zero only because voltage drop across the switch is taking place now. This VSW is non-zero and this ISW is also non-zero during the on state. Okay, so that's why this power loss is a non-zero. This power loss is a non-zero, right? But whereas in the ideal case it was a zero now. In the ideal case it was a zero, right? So, but definitely this value is small. This value is a small value. Why small value? Because even though the current is high, but what about the VSW? VSW is very small voltage, na? It is like a on state voltage drop, right? So that's why this value will be small value, right? Similarly, if you check for off state, second one, during off state, yes, during off state, the power loss is equal to VSW during off state into ISW during off state. So during off state, VSW is a high value, no doubt. What about the ISW? ISW is a leakage current, na? Right? So that high voltage into leakage current. Leakage current is in the range of microampere, I said. Okay. So therefore that product will be again small value, right? But it is a non-zero. So P is not equal to 0. So therefore, and this value is a small value again. Small value. So always keep it in mind. The practical switches always causes, yes, non-zero power loss during their on state as well as during their off state. Okay, they have asked the questions. Simply they will give you the voltage across the switch, current flowing through the switch during the on state or during the off state, and they will ask find the switching losses. Okay, find the switching energy. So how to find it? We are going to discuss, right? So this is during on state and off state. Next, what about the behavior of the practical switch during the transition state? Let us discuss. During the transition state, let us put the heading third one, transition state. Transition state, yes. So transition state, in that, let us first discuss the turn on transition, and next after that we'll discuss the turn off transition. Okay, so turn on transition. As I said, turn on transition means initially switch was in a off state and now it is a turning on. Now it is a turning on, right? So how is the plot? The plot will be like this. Correct. So time t 0. Let us consider this as a voltage across the switch. Suppose this is a current flowing through the switch. This is a time t, right? This is a time t, and this is your control signal. Okay, control signal. Now switch is in a off state and we are interested in turning it on. That is the turn on transition, right? So here the plot means here it should be the control signal. Control signal we have applied. So at this instant, yes, it is expected that the ideal practical switch should turn on. Okay, so here this is a control signal. Control signal. Yes, ISW, that is the current flowing through the switch, and the VSW, that is the voltage across the switch, right? So before this point, it is like a switch is in a off state. After this point, it is like a switch is in a on state, right? Switch is in a on state. Now, when switch is in a off state, the current flowing through the switch is leakage current, right? Current flowing through the switch is leakage current. So the current will be a very small here during the off state. Current flowing through the switch is very small. That is a leakage current. This is a leakage current, right? This is a leakage current. Now, as soon as this control signal is applied, yes, what will happen? The current flowing through the switch starts increasing. It will not become zero suddenly. Okay, right? It will start increasing slowly. And the rate of increase of current, it depends on your circuit parameters. It depends on your circuit parameters. Okay, because we know na current in the circuit, once switch turns on, the current in the circuit depends on circuit parameters, right? So therefore, a rate of increase of current, it depends on the circuit parameters. And after that, it reaches the steady state. After that, it reaches the steady state, right? So let us consider the steady state value is a I. Steady state value is a I, right? Similarly, you can check the voltage across the switch. When switch is in an off state, what is the voltage across switch? It is a high voltage, na? Right? So let us consider the high voltage is this one. This is a high voltage when switch is in an off state. Okay, so here it is an off state, right? And next, after this, we can say it is an on state. So this, what will be the transition, turn on transition, those things we will discuss. Okay, so next, what will happen? Yes, as soon as the control signal is applied, yes, voltage across switch starts decreasing. It will not suddenly become zero. In an ideal switch, it was changing from non-zero to the zero value in a zero time, na? But it is not true in a case of practical switch, right? So therefore, it will take some time. It will take some time to reach the voltage. Okay, this voltage is equal to your on state voltage drop of the switch. This voltage is what? On state voltage drop of switch. Okay, so generally in diode, that voltage is 0.7 volt, na? Means this voltage, it is on state voltage drop. Okay, so now here you can check from this point. Initially this switch was in an off state, right? After this instant, we can say that after this instant, you can check the current is a non-zero. It is a high current, and voltage is a very small, that is a leakage current. So can we say that here we are having the switch is in an on state, here it is in an off state. So between these 2 points, that is a off and on, what it indicates? It indicates your turn on transition of the switch. Are you getting the point? It indicates the turn on transition of the switch, right? So let me write it as, this is a turn on transition of the switch. This indicates turn on time. Turn on transition time. Is this clear? Turn on transition time. This time was zero, na? In case of ideal switch, this time was zero. But whereas in this case, this time is non-zero, right? So that's why power loss during the turn on transition, it will be again non-zero, na? Right? Because you can check during this time interval, the current is increasing, voltage is decreasing. Okay, this is current is increasing, voltage is decreasing, both are non-zero. So therefore power loss will be non-zero only, na? Right? Power loss will be non-zero. So let me write here, in practical switch, yes, turn on transition time is a non-zero, right? In ideal case, it is a zero, right? But in a practical case, it is a non-zero, right? Always keep it in mind. It is a non-zero, right? Next, what about the power loss during the turn on transition? Again, it is a non-zero, no? Because time is non-zero, voltage is decreasing, voltage is decreasing, current is increasing, right? So if you take the product, yes, after this we'll discuss about the how to find the energy loss and those things. Okay, for this curve actually, right? For this curve. So this is about the turn on transition of the switch. Next, let us discuss the turn off transition. Turn off transition. Yes. So during the turn off transition, what will happen? Initially, switch is in an on state. Consider this is VSW. Here it is a time T. This is the ISW. Time T, and here we are in the control signal, right? So initially switch is in a on state, right? Suppose this is a control signal, and at this instant the control signal is removed. Okay, so this is a control signal. So during this interval, it is like a switch is in a on state. After this, we are interested in turning it off, right? At this instant, we are interested in turning it off, right? Next. So here, when switch is in a on state, what is the current flowing through the switch? It is a high value, right? So current flowing through the switch will be high value. So this is a high current. As soon as the control signal is removed, what will happen? The current flowing through the switch go on decreasing. It will not become zero in a zero time, na? It will take some time, right? It will take some time. So it will go on decreasing. And next it will reach this current. And what is this current? This current is your on state, this is a off state leakage current, right? Off state leakage current. Let me write it as a leakage current. Okay. Similarly, in the case of VSW, initially switch is in on state, so voltage across switch will be very small, na? It is an on state voltage drop. This voltage is very small. This is a on state voltage drop across the switch. As soon as the control signal is removed, yes, voltage across the switch starts increasing. Voltage across the switch starts increasing. And after this point, it becomes a steady value. This is a V. This is a V. This current is the initial current. It is a I. When switch was in on state, current was high. When switch is in an off state, the current is low, voltage is high. So can we say that this indicates the off state of the switch? This is the off state, right? This indicates from here to here. It is the on state of the switch. On state of the switch, right? And in between, whatever the time we're having, it is like a turn off transition, right? Turn off transition time, okay, of the switch. So let me write it as turn off transition time, right? Turn off transition time. So here in the practical switch, the turn off transition time is non-zero. Generally, it is a very small. Generally, the value is a very small. Okay, it is in the range of milliampere. No, sorry, millisecond. Okay, or the microsecond even, right? So, but it is a small. But as this time is a non-zero, so therefore it causes some power loss, because during this interval, if you check, voltage is like current is like this non-zero, voltage is also non-zero. So that's why the product, if you take, the power loss will be non-zero, right? So let me write practical switch. In practical switch, yes, turn off transition time is a non-zero, whereas in case of ideal switch it was zero, but here it is a non-zero, right? Here it is a non-zero. Next, so what about the power loss during the transition time? Transition means turn on transition plus turn off transition. Okay, so power loss during transition state. Can we write it is equal to power loss during turn on transition plus power loss during turn off transition plus power loss during turn off transition. Right? So power loss during turn on transition is VSW into ISW. VSW into ISW. Both are non-zero, na? and here it is also VSW into ISW, right? So therefore it is a non-zero. So power loss during transition state, okay, and it is also known as a power loss during the switching. Let me write it as a switching power loss. Switching power loss. Switching power loss. Right? Sometimes they ask the question, find the switching power loss. Means it is expected that we need to find the power loss during the transition state. Okay, they will give whether it is on or whether it is off. Okay, or sometimes they ask the power loss, total power loss. Means we need to find the power loss during the on transition and the power loss during the off transition, right? And we need to add those. Okay, so the difference till now, whatever we have discussed, if you check ideal switch, on state voltage drop is 0, right? Next, ideal switch during the off state, yes, current flowing through the switch is 0. In the case of practical switch, on state voltage drop is non-zero, it is a very small, right? In the case of practical switch, the off state current flowing through the switch is very small, it is a leakage current, right? That is a leakage current, right? Next, during the on state ideal switch, power loss is equal to 0. During the on state practical switch, power loss is non-zero. During the ideal switch, off state power loss is 0. Practical switch, off state power loss is non-zero. Ideal switch transition state power loss is 0. Practical switch transition state power loss is non-zero. Okay, so these are the differences, right? Next, the next one we are having the external circuit requirement. External circuit requirement, right? Next. Yeah. I will solve that question later on. Don't worry about the question solving. Okay. Let me first cover the sufficient theory which is required, okay, to solve the question, right? So next one is the external circuit requirement. External circuit requirement. So the practical switches requires the external circuitry to turn on the device and to turn off the device as well. Okay, means practical switches requires the external circuitry to turn on, and those circuitries are known as the triggering circuit. Okay, let me write it as triggering circuit. Triggering circuit, or it is also known as a gate drive circuit, or it is also known as a base drive circuit. Base drive circuit. The name varies with respect to the switch. Okay, if you check the BJT, then there will be the base drive circuit. Okay, in the SCR, we are having the gate drive circuit, right, etc. So triggering circuit or gate drive circuit or base drive circuits, okay, required to trigger the SCR, to trigger the switch, to trigger the practical switch. Practical switch, right? Second, commutation circuitry. Commutation circuitry. Is required to turn off the switch, to turn off the practical switch. This is a generalized statement. Again, I am saying, okay, we are having some switches, those even doesn't require the commutation circuitry. Okay, but triggering circuit is required, like this we are having. Okay, so again, depending on that, we are having the different types of the switches, right, that we are going to discuss after some time. That is uncontrolled, semi-controlled, fully controlled, those things, right? So yeah, so triggering circuit is required in the practical case, as well as the commutation circuit is also required in the practical case. But whereas in the ideal case, if you check, In the ideal case, yes, external circuit requirement was not there, right? Now, the last point, that is the thermal stability or constraint. Thermal stability or constraint. Okay. So, right. Current flowing through the switch, voltage across the switch. This is a VSW, voltage across switch, and here it is ISW, current flowing through the switch. If you check during the on state, the current range, okay, allowed current range, whether it is a finite or infinite, in the case of practical switch, it is a finite, na, right? So it was from like plus I dash till minus I double dash, na. So it is a I dash till minus I double dash. But whereas in the ideal switch, it was like plus infinity to minus infinity. In practical switch, we are having the finite limit. Okay. Similarly, in the case of voltages, right, that is during the off state. So voltage blocking capacity, yes, it is like a plus V dash, and here it is a minus V double dash. We have written. Okay. Next. So if you take here, it indicates the maximum allowed current, that is a current limit. This is a voltage limit we are having for our practical switch. This is a current limit, right? So this is a, yeah. Correct. This indicates the voltage limit for the practical switch, right? This also indicates the voltage limit in the reverse bias. Voltage limit. What is the reverse bias, and those things we will discuss. Next, current limit for a practical switch. This is a current limit, right, in the reverse bias or the reverse direction. Current limit. Okay, so this is the area we have denoted, okay, by considering the voltage and the current limits, voltage and the current limits. But if we operate the practical switch at these corners, corresponding to this, the VI current is at the upper limit, voltage is also at the upper limit. So that's why it will cause a high power loss. Okay. So from the manufacturer side, okay, by considering the device safety, generally the manufacturer will give the limits like this. Means the limit for voltage across the switch and the current flowing through the switch, which is somewhat lesser than that of what is the Imax in the forward and the reverse, as well as Vmax in the forward and the reverse. Okay, so these are given by the manufacturer, right? I am saying here it is like this, here it is like this. Means compared to the actual value, allowed value, the manufacturer says that yes, it is better to operate the switch less some very lesser value. Okay, this difference between this point and this point, it is a very small. Okay, so manufacturer says that operate the switch to the somewhat lesser value, okay, than that of the maximum value. Okay, so for same values for voltage as well as current. Next, here it is a current, and here it is a current in the reverse direction. Okay, and yes, here we are having the power limit also. And that power limit, because we know now, when the switch causes the power loss, its heat will be generated. When the heat is generated, the temperature will increase. And our semiconductor devices are very sensitive to the change in the temperature, right? So, yeah. So here we are having the limit like, yes, this, if I join these 2 points, it will be like this. This will indicate your power limit. Okay, so the power limit. Power is nothing but what? Product of voltage and current. So it indicates your SOA, safer operating area, and it is given by the manufacturer in the data sheet of the switch, data sheet of the device. Okay, so This is available in a data sheet. So you can check the difference between ideal switch and practical switch. Ideal switch was thermally stable, okay, on a entire VI plane. But whereas if you check the practical switch, it is having some constraints. Na? Why these constraints are there? Due to a practical, as the practical switches are causing the power losses, na? And due to that the heat is generating. So that's why it is having some thermal constraints, right? Thermal constraint. So this is about the difference between the ideal switch and the practical switch and the concept switch right? Next, let us move towards the next point. Yeah, transition behavior of switch. Transition behavior of switch. Yeah, please check whether it is visible. Yes. Okay. Thank you. Yeah. So transition behavior of switch, right? Transition behavior means what? Behavior of switch during the transition state. Okay. Behavior of switch during transition state. Behavior of switch during transition state. So we have discussed the transition behavior. What will happen to the voltage across the switch and current flowing through the switch, okay, during the turn on transition and during the turn off transition. Let us first of all recall those points here, right? So what we discussed during turn on transition, during turn on transition, what about voltage, whether it increases or decreases? During turn on transition, yes, voltage across the switch, it increases or decreases? It decreases, na, right? Turn on means initially switch is in off state, right? So that's why while turning on, okay, its voltage goes on decreasing, right? So voltage across switch decreases. Voltage across switch decreases. Now what about the current flowing through the switch? Current through switch, it increases, right? Current flowing through the switch is increases. Same thing we have discussed, right? Yes. Next, similarly, during the turn off transition, yes, voltage across switch increases and reaches the steady value, no? Right? And what about the current through the switch? Current through switch is decreases, right? It decreases. Yes, it decreases. Now suppose, yeah, let me draw one plot here. Time t. Suppose this is VSW, this is a ISW, and the plot is like this. Suppose this voltage is P volt. And suppose this current is I ampere. This current is I ampere. Now, yes, I have drawn a plot for voltage across switch and current flowing through the switch. Okay. So by observing this plot, can we find the turn on transition and turn off transition corresponding time? My question is, by observing this plot, can we find the turn on transition and turn off transition? Yes, you can check here. Before this instant, voltage across switch is 0. Current flowing through the switch is high value, right? Means can we say that switch is in a on state here, right? So can we say that here the switch is in a on state, means it is like the on state voltage drop of the switch is considered as a 0. On state voltage drop of the switch is considered as a 0, right? Because it is a very small, na? Hardly 0.7 to 1.5 volt drop is there. So it is like neglected, and that's why this is like a on state. Next, you can check after this point, from this point to this point, if you check, the voltage is non-zero, current is a 0. Voltage non-zero, current is 0 means what? Yes, it is like a switch is in a on state, sorry, switch is in a off state, voltage is non-zero, that is a high voltage, and current is a 0 means what? Switch is in a off state. Okay, so this indicates the off state of the switch. Off state of the switch. Next, again you can check, so between on and off, what state we are having? This state is nothing but, yes, turn on transition state. Yes or no? Right? This indicates the turn on transition. Right? So let me write this time as TR. Let me indicate this time as a TR. Let me indicate this as a TR. Right? This as a TR. Next, you can check here from this point to this point. Voltage is decreasing, current is increasing. So can I say that this indicates, yes, this indicates the off transition of the switch, right? Let me write it as a TF. TR is nothing but your time corresponding to the on transition. TF is corresponding to the time corresponding to the off transition. Time corresponding to the on transition, time corresponding to the off transition. Is this clear? Are you getting the point? Right? So let me write time corresponding to the on transition and time corresponding to the off transition, right? So yeah. So TR, it indicates the turn on transition time. Turn on transition time. Next, TF, it indicates turn off transition time. Turn off transition time. Right? Now, related to this, we are having the concept of energy loss. Okay, energy loss during the turn on transition and the energy loss during the turn off transition. Okay, so let me write energy loss during the turn on transition and energy loss during the turn off transition. Sorry. TR is the turn off. Yes, definitely this should be the turn off. Yeah, this should be the turn off, and here it is a turn on, right? Because on to off, so that's why it is a turn off. Off to on, so that's why it is a turn on, right? So yeah. So TR, turn off transition, TF is the turn on transition. Now let us find the energy loss. Okay, energy loss during the turn on transition and energy loss during the turn off transition. So let me write energy loss. First, let us find during the turn on transition. Energy loss during turn on transition. Turn on transition. This is our title. We need to find the energy loss, right? So here, what is the energy? Energy is nothing but the integration of power. And what is the power? Power is nothing but the voltage across the switch into current flowing through the switch. Yes or no? Right? So here, first of all, we need to find the expression for, yes, the VSW during the TR and ISW during the TR. Then and only then we can find the energy loss during the turn on time. Energy loss during the turn on time. Right? So let me write. Yes. So energy loss during turn on time. So it is equal to E during turn on. Okay. Is equal to integration. Yes. we will put the heading, we will write it as a 0 to turn on time is, you can check only 0 to TR na, this is a turn on time. So this time is TR means if I consider this as a 0, this will be like your TR. Okay, so it will be like integration from 0 to TR. Next, what is the yes, VSW and ISW we need to write into dt. Integration of power, V into I means power. Integration of power is nothing but the energy. Integration of power means the energy, right? So now we need to find the expression for VSW. VSW expression we need to write. So during TR, let me write during the TR. Please be careful. This is very important. How to write the expression of TR, VSW and ISW. That is very important. Okay, so during TR, VSW is equal to, now you can check the VSW waveform. During TR, this is the VSW waveform we're having, right? So during TR here, yes, if VSW is this waveform and this slope is linearly increasing, okay, this slope is linearly increasing, okay. So can we say that as this slope is linearly increasing, so can we say that the expression will be y is equal to m into x, where m is nothing but the slope na, and y is nothing but your VSW, x is nothing but the time, right? So let me write it as, during TR, sorry, this should be the turn off. TR is a turn off na, so that's why this is a turn off. I am sorry, please consider this one. This should be turn off, not the turn on, right? This should be the turn off because TR indicates the turn off transition, right? So now, yes, during TR, what is the VSW? So we need to write the expression for this VSW, As this is linearly increasing, we know for linearly increasing function, what is the expression? Y is equal to m into x. In our case, y means what? It is a VSW. This is a VSW is equal to m means what? It is a slope na. So what is the slope? Change in the y divided by change in the x. That is nothing but the slope. So from this point to this point, that is during TR, what is the change in the VSW? Change in the VSW changing from 0 to the V na. This indicates this is a V. So 0 to V means change in the VSW is a V. So it is a V divided by, what is the change in the time? Change in the time is TR na. So divided by TR. VSW divided by TR. Into what? Yes, it is x. X is nothing but the time na. So into t. So VSW is equal to V into t by TR. This is the expression for voltage across switch during the TR. Voltage across switch during the TR. Is this clear? What I have written? Simple y is equal to mx, because slope is linear, slope is increasing na, linearly increasing. And for linearly increasing function, we know y is equal to mx, and m is nothing but the slope. This m is nothing but the slope. In our case, y is nothing but VSW and x is nothing but the t na. Y is VSW, x is a t, right? So let me write it as VSW is V by TR into t. V by TR into t, right? V by TR into t. This is your VSW. Similarly, during TR, can we write the expression for ISW? ISW expression during TR. Yes, you can check ISW, this plot. During TR means this time is TR we are having. This time is TR. So during TR, you can check ISW is decreasing. It is a linearly decreasing. So if the linearly decreasing, so what about the slope? Slope should be negative. Slope should be negative, right? VSW was increasing, so slope was positive. Now it is a negative. Slope is a ISW is decreasing. So ISW decreasing means slope is negative. So how to write the expression for this plot? Let me write here first V by TR, this one here, into T. This is whatever we have written here, right? So this is for VSW. Okay. Next, ISW. Let us write for ISW. So how to write for ISW? Please listen. This is very important. Slope is negative, na? Slope is negative. So same here. Y is equal to minus mx. Okay. So y is nothing but your ISW is equal to minus as it is. Slope you can check. What is the change in the y? Change in the y is equal to ISW minus 0. So it is ISW. Change in the x is TR. Change in the x is TR. Okay. Into, it is a t, into t. Let me write here, into t. But only writing this is not sufficient, because here you can check the current is decreasing from the I na. So we need to add the plus I also here, plus I also here. Now you can check both the expressions. You can check both the expressions. This expression VSW is V by TR into T. This is valid only during this interval. This expression of ISW, that is the plus I minus ISW by TR into T, this is valid only this interval, for this interval. So you can check if this time is TR and if I consider this time as a 0, I am considering this time as a 0. So can I say that this time will be equal to TR? Is this clear? This total time is TR, and if I consider this time as a 0, then this time will be equal to TR, na? Right? So now here you can check as the at T is equal to 0, you can check at T is equal to 0. So here if you put T is equal to 0, what is the VSW? It is a V into 0 by TR. So V into 0 by TR means 0. So here you can check VSW value is 0 here. After that, you can check as TR increases, na, from here to here, it is a TR increasing. As TR increases, this T increases. So that's why your VSW increases. You can check at T is equal to TR by 2. TR by 2 means this full is TR. So TR by 2 means what? Exactly the 50% of this TR, na? 50% of TR means this TR by 2. Corresponding to this instant, what is the VSW? You can check here at T is equal to TR by 2. If we put T is equal to TR by 2 here, VSW is V into TR by 2 divided by TR. TR cancel out. It will be V. It will be like a V by 2, na? So V by 2 means exactly at the center point. Again, you can check at T is equal to TR also. If you put here T is equal to TR, you will be getting V by TR into TR. TR will get cancelled out. So it is a V only. So that's why it is a V. Right? Means this expression, whatever you have written, right, is a true, is a correct. Similarly, you can check for the ISW also. For ISW, how I have written the expression, please listen, this is important, right? So for that, first thing is we have added the initial value because current is decreasing from this plus I, na, right? So that's why here plus I we need to add. Next, the slope is negative because it is a decreasing, na? So slope is negative. So slope is nothing but it is like change in y divided by change in x. So we have written it is minus ISW by TR into T, right? Into T. So you can check here. This is TR. So consider this is a 0. So therefore this will become TR, na? This will become TR, right? So at T is equal to 0, you can check at T is equal to 0. It will be like this term will become 0. It will be only plus I. So that's why it is a plus I, right? As a T increases, this negative term increases, this difference decreases. So this difference is decreasing. At T is equal to TR, you can check at T is equal to, this is TR, na? If this is 0, this will be TR. Okay, at T is equal to TR, you can check minus ISW by TR into TR. So TR cancel out. So it is like a, yeah, it should be minus I. Minus ISW not. It is minus I, na? Change in the current is minus I, na? Right? So correct. It is a minus I. Here it was a V, na? So here it is minus I. So TR cancel out. So it is plus I minus I. It will become 0. So it is a 0. Right? So in this way, we can write the expression for VSW and ISW. Slope is positive, slope is negative. Okay. So now VSW, ISW expressions we are having. So how to find the energy loss? How to find the energy loss? Let us discuss. Yes. So now how to find the energy loss? So ISW, let me write it is minus I by TR into T, minus I upon TR into T plus capital I, plus capital I. Right? Now simply VSW, ISW we need to put here. Okay. So therefore I am writing, therefore energy loss during T off, energy loss during the off transition, na, is equal to what? Integration over 0 to TR, right? And what is the VSW? It is a V by TR into T into, this is equal to minus I upon TR into T plus current I into dt, right? Now we need to simplify it. Here it is a V multiplication we are having. Here it is I. So can I take V into I outside? Yes, we can take V into I outside. So therefore ET of is equal to V into I. If I take it outside, it will be like integration over 0 to TR, right? So it will be T by TR, correct? T by TR into this T by TR na, if I multiply. So let me write first, it is like this, minus T by TR plus 1 na, because I have taken this I, full I outside. So it will be minus T by TR, and this V also I have taken outside. So it is a T by TR, okay, into dt. So if we multiply this term, so it is equal to V into I into, it is like integration from 0 to TR. It is like a T by TR into minus T by TR. So it is like a minus T square by TR square na, minus T square by TR square, right? So minus T square divided by TR square. Let me write it as into dt, right? Plus integration from 0 to TR. It is like a T by TR into dt, correct? So next we can write it is equal to V into I into integration of T square, T cube by 3. So that we can write it as a T cube by 3 into TR square as it is. Limit will be 0 to TR. This is the one thing. Minus should be there. Okay. And here it is a plus. Yes, we can write it as a T square by 2 TR. And limit should be 0 to TR. Correct? Integration of T is T square by 2. Integration of T square is T cube by 3. Right? So after putting the limit, we can write V into I into, it will be like minus TR cube divided by 3 into TR square. Okay? Plus the TR square divided by 2 into TR. So you can check TR square 1 will get cancelled out. This TR and this TR will get cancelled out. So it is like a V into I into, it is like a, yeah, minus TR by 3 plus the TR by 2 na, minus TR by 3 plus the TR by 2. So we can write it as a V into I into, this can be written as a, yes, 3TR minus 2TR, that is a TR divided by 6 na. So which is equal to V into I divided by 6 into TR. This is the energy loss during the on time. So always keep it in mind. If you are having the function like, okay, like one is decreasing, second one is increasing, one is decreasing, second one is increasing. Okay, so this formula is very important. Okay, you can simply, yes, keep it in mind, simply keep it in mind. Okay, students are messaging, but those messages are not. Am I audible? Off time, right? Off time, correct? Yes. Okay, so yes, okay. So next, this is the energy loss during the off time. Energy loss during the off time. Next, similarly, can we find the off time means what? It is a turn off transition, I am saying. Okay, next, energy loss during the turn on transition, can we find? Yes, energy loss during the turn on transition. Energy loss during turn on transition. Turn on transition. Yes. So during turn on transition means during what we have written TF na. Turn on transition means we are having this time na, off to on. So that's why during TF we have written. Okay. So during TF during TF, we need to write the expression for this decreasing voltage and increasing current. Current is increasing linearly, voltage is decreasing linearly, right? So can we write the expression for the current during turn on transition, that is during TF? Current is increasing linearly, this value is capital I, na? This value is capital I. So slope is equal to, yes, I divided by this TF. If this is TF, definitely this will be TF, na? This will be TF. So let me write it as a current ISW is equal to capital I divided by TF into T, right? So during TF, ISW is equal to capital I divided by TF into T. This is your ISW. What about the VSW? VSW is a linearly decreasing, na? It is a linearly decreasing. So what is the expression for this one? Slope should be negative, and again we need to consider the initial voltage V also. So it is a V minus this V divided by TF into T, na? In the same way, whatever we wrote for ISW, na, during TR, I have written VSW during TF. This is your VSW. Let me write it as VSW. This is a VSW, right? So you can check. So VSW is V minus V by TF into T. So V minus V by TF into T. This is a VSW. Now we need to find the energy loss during TF, right? So let me write energy loss. Therefore, energy loss during turn on transition. So it is a ET on, right? Turn on transition energy loss. Again, it is integration over 0 to TF. 0 to TF. It is a VSW into ISW into DT. Integration of power is nothing but energy, right? So integration over 0 to TF, VSW, ISW into DT, right? So therefore we can write ET on is equal to integration over 0 to TF. What is a VSW? It is a V minus V by TF into T. V minus V by TF into T into what is a ISW? It is a I by TF into T. I by TF into T into DT, right? So again we can take V and I outside. So it is equal to V into I into, let me write it as integration over 0 to TF. Yes, that will be 1 minus T by TF into T by TF into DT, correct? Further, we can take the multiplication. So it is equal to V into I into, yes, this can be written as integration over 0 to T, T by TF into DT minus integration over 0 to TF, no? 0 to TF, that should be, yes, minus is there. So it is a T square divided by TF square. T square divided by TF square into DT, correct? So it is a T by TF and minus is here. So T by F, T by TF, T by TF, T square by TF square. So next we can write V into I into, this can be written as, let me use the curly bracket. So T square by 2TF, limit 0 to TF, minus this will be T cube divided by 3TF square, limit 0 to TF, right? So it is equal to V into I into, we can write it as TF square divided by 2TF minus TF cube divided by 3TF square. So it is TF cancel out, 2TF, that is TF square cancel out. So it is equal to V into I into TF by 2 minus TF by 3, na? So again it is 3TF minus 2TF, that is TF divided by 6, na? So V into I divided by 6 into TF. This is your energy loss during turn on transition. So it is a ET on. So again, you can check both the expressions. Both the expressions are same. Both the expressions are same. So if simply they give the plot like voltage across the switch, right? During this interval, if voltage across switch is linearly increasing and second one is a linearly decreasing, then always keep it in mind, energy loss is equal to 1/6 into voltage V. That voltage V means what? This voltage. Current I, capital I means what? This current. Are you getting the point, right? Into respective time, that is TR or TF. Okay, if we want to find the energy loss during TR, then it will be into TR. If we want to find the energy loss during TF, it will be into TF, right? So this is energy loss during turn on transition and turn off transition. So therefore, what is the total energy loss during the switching transition? Energy loss during the switching transition. Energy loss, therefore, energy loss during switching is equal to ET on plus ET off. Plus ET off. Okay, so ET on is we know it is equal to, it is also known as the switching loss. Energy loss during switching means what? It is a switching loss. Okay, so it is a V into I/6 into TF plus V into I/6 into TR. So this can be written as V into I divided by 6 into TF plus TR. TF plus TR, right? So this is the switching loss or energy loss during switching. Okay. During switching. Correct. Vi/6 into TF plus TR. So if this is the energy loss, how to find the power loss? We know na, power into time means energy. So energy divided by time means what? It is a power. Okay. So which time we need to consider? We need to consider the switching time. We need to consider the switching time. Means if they generally they give the frequency, switching frequency. So from that we can find the switching time. Okay. So let me write power loss, or let me write switching power loss. Switching power loss is equal to energy loss divided by time. Energy loss divided by time. But this time is switching time. This time is a switching time. Switching time. Okay, switching time. That is nothing but your TS. And switching time TS. TS is equal to 1 by switching frequency. What is the switching frequency and those things I will elaborate during the numericals. Okay, switching frequency. Fs is the switching frequency, right? So Fs is switching frequency. They will give the switching frequency just like 100 kilohertz, 1 kilohertz, like this. Okay, so accordingly we can find the switching time. And once we find the switching time, so we can find the power loss. Okay, switching power loss. Is this clear? So always keep it in mind. If they give the functions like one is linearly increasing, second one is linearly decreasing, then here we need to keep this expression in mind. Or second way is you can simply write the expression. You can simply write the expression for that respective curve, linearly increasing, linearly decreasing, and you need to simplify it. Right? The choice is up to you. In order to save the time, you need to memorize this expression. Right? Okay. So this is about the transition behavior of the switch and the energy loss during the switching transition, and as well as the power loss we have discussed, right? Next, let us move towards the average and RMS value of a function. Means how to find the average value and the RMS value of a given function. Let us discuss. Okay, so So here in this section, we are going to discuss the expressions for average and RMS value of the triangular function, RMS and average value of the rectangular function, Cauchy square wave like this, like function if we are having. Okay. So first thing is average value. Average value. Suppose we are having a function y is equal to f of t. Suppose we are having a function y is equal to f of t. You can unmute and speak. Those who have raised the hand. Yes. Okay. Vishwanath, you have mentioned that y is equal to mx plus c. We'll discuss it at the end of the session. Okay. That c is like your initial value. So average value y is equal to f of t. Suppose we are having the function y which is equal to f of t. Okay. So we are having a function which is represented as f of t. This is the function of the time. Okay. Function of the time. So how to find the average value of this function? How to find the average value of the function? Yes, that is the average of function y. Average of y is equal to 1 by t integration over 0 to t f of t into dt. F of t into dt. This is the average value, right? So if we are having the function y is, let me write it as a function y is a periodic function with a periodicity capital T. Means y is what? We are having a periodic function and it is having a periodicity of a capital T. Then how we find the average value? It is a 1 by t integration over 0 to t f of t into dt. Integration means what I am doing? Integration is nothing but I am adding all the instantaneous values over the 0 to time t, 0 to 1, that is a 1 period. Okay, we are adding the instantaneous value and again dividing with the, yes, what is the periodicity of the function, right? That is the average value. Now one more thing, what this integration indicates? Can I say that this integration is nothing but the area of the function? Can I say the integration is nothing but the area, right? So it is the area of function f of t. Area of a function f of t. Means suppose if they give a simple function, if they give a simple plot, okay, of a rectangular waveform, then it is better to find the average value. Yes, first of all by finding the area, because for rectangular function we know area is nothing but length, okay, into whatever that height will be there. Okay. So simply we can find the area and again divide with the periodicity. You will be getting the average value, right? Average y. So this is the average of a, yes, periodic function. We are having 1 by t integration over 0 to t f of t into dt. And this integration over f of t, integration over 0 to t f of t dt, it indicates the area. It indicates the area of the function f of t, right? Next, this is the average value. Now, what about the RMS value? RMS value. RMS value of suppose function y. Again, y is equal to what? It is a f of t. This function is a periodic. Y is periodic function with periodicity capital T. With periodicity what? Capital T. Then how to find the RMS? What this RMS stands for? RMS means root mean square, na? It is a root mean square. Root means what? Square root of mean. Mean means average of squared values. Square root of mean of squared values is nothing but your RMS. Okay, so how to find the RMS value of y? So RMS of y, RMS value of the function y is equal to, how to find? Here in the average, during the average, we took the, yes, integration of f of t, na? But here we are interested in taking the average of squared values, and after that we need to put it into the square root, na? So it will be like 1 by t integration over 0 to t, that will be like your f of t square into dt and to the power 1 by 2. Let me write what this indicates. Please try to understand this expression. Square root of mean of squared value, na? We are integrating the squared values and again dividing with the time. Means what? This indicates the average of the squared value, and again I am putting it into the square root. So that's why it is a square root of mean of squared value. Means what? It is the RMS value. Means what? It is the RMS value. Is this clear? Right? So in this, what we are doing? Yes, we are doing, it is like we are taking the integration of f of t square. Means what? F of t square we need to do, and we need to integrate. Means what? It is like a area, na? It will give you the area. It will give you the area, right? So let me write it as, yes, let me highlight this. This integrate, this integrate. Yes, RMS of y is equal to what? This indicates, this indicates average of f of t square, na? F of t square, and again to the power 1 by 2. F of t square average, and again to the power 1 by 2. That is a square root. That is a square root. Okay. So average of f of t square means what? It is the area, na? Again, it is a area again, right? So same thing. Now let us discuss one by one some numericals. We are going to discuss how to find the average value and how to find the RMS value, right? So yes. The current through and voltage across a switch are shown in the figure. Find average current, RMS current, and average power loss. Okay, that we need to find. So let me first indicate here current here I. They have given, this is a given data.
RMS current.
This is 10 ampere. This is a T by 2. Here it is a T and 3T by 2. This is the voltage they have given. This is the 1 volt. It increases to the peak value. Correct. This value they have given as a V. Okay, this value is a V. This is a V, and this one is a 1 volt. This is a 1 volt. Okay, so our task is to find, this is T by 2, this is the T, and here it is a 3T by 2. Current waveform is given, voltage waveform is given. The current through and voltage across the switch are shown in figure. That is V and I. These are the voltage across switch and current flowing through the switch. Find the average current, RMS current, and average power loss. Average power loss we need to find. Okay. Average current, first of all, let us find. How to find average current? I average. Average current. In both the ways, I will show you. One is by considering the area, and the second one is taking the integration. Okay, in both the ways you will be getting the same answer. Okay, so now this is the triangular function, right? This is a triangular. Whether current I is this waveform is a periodic? Yes, na? Because whatever the waveform we are having from 0 to t, the same is repeating from t to 2t. Same will repeat from 2t to 3t and so on, right? So first of all, let us find by considering the area only, right? By considering area, how to find the average of this? Simply we need to find the area, right? And again divided by what we have written. You can check here. What I have written, this is a area divided by the periodic time, na? That is a periodicity. Area divided by periodicity. So let me write it as, yes, I average is equal to area under current I, right? Divided by periodicity is T, na? Periodicity means what? This indicates periodicity, na? From here to here, this is the periodic time. So this will be the periodicity. Because whatever the function we are having from 0 to t, the same is repeating from t to t to 2t. Same will repeat from 2t to 3t, right? So that's why periodicity is your t. Periodicity is capital T. So right, area under this curve, that is the I, area under this divided by this periodicity we can write. So how to find the area? This is very simple, na? How to find area? It is a 1 by 2 into t by 2 into 10, right? 1 by 2 into t by 2 into 10. 1 by 2 into t by 2 into 10 divided by t, na? So here tt will get cancelled out. So it is equal to 10 by 4. 10 by 4 is equal to 2.5 ampere. This is a I average value of current I. What I have done, simple, I have taken the area divided by the periodic time t. This is the one method. Or second method we are having is, what is the second method? The second method is, we need to write the expression for this current. You can check. We need to write the expression for this current. And again, we need to write 1 by t integration over 0 to t, and we need to put this expression. That will be a lengthy procedure. But you can check in both the ways, you will be getting the same answer. Okay, so this is actually shortcut. Whatever I have written now, the area divided by t, this is a shortcut actually, right? Shortcut. Is this clear? Yeah. You can simply check if we find the expression for this plot. This is linearly increasing now. So what will be the expression? It is a I is equal to change in the y, that is a 10, divided by change in the x, that is a t by 2 now, into time t. So it is equal to 20 divided by t into t. This is the expression for current I. Now in order to find the average value, what we need to do? Yes, or this is the second method. I average is equal to 1 by t integration from 0 to t. This is the I into dt. But from 0 to t, will you please mute your mic? Yes. So from 0 to t, we are having two intervals, na? 0 to t by 2 and t by 2 to t. Right? So here we can write, yes, it is equal to 1 by t integration from 0 to t by 2. What is the value of current I during 0 to t by 2? It is a 20 by t into t, right? 20 by t into t. So it is a 20 by t into dt, and plus what from t by 2 to t, from t by 2 to capital T. What is the value? It is a 0. So value is 0 means what? It is a 0 into dt. So this term will become 0. The only this term we need to find. So it is equal to 20 divided by t square into, what is the integration of t? T square by 2. Yes. So t square by 2 limit is 0 to t by 2. So you can check, it is equal to, yes, 10 divided by t square into t square divided by 4, na? So t square cancel out. So it is 10 by 4. Again, it is a 2.5 ampere, right? This will be your IT average. That is I average. You can check in both the ways, you'll be getting the same answer. But which method will give you the quickest in quickest time? That is this one, na? Area we need to consider first, right? Yes, disturbance now I have removed, right? So now this is about the average current. Next, how to find the RMS current, right? How to find the RMS current? Yes, for that we need to write, yeah, IRMS. Let me simplify it, IRMS. We can first simplify it by the expression, and after that at the end we'll be getting one expression or one shortcut. Okay, that I will tell you. So it is IRMS is equal to 1 by T integration from 0 to T by 2 na, because from 0 to T the effective interval is only T by 2. From T by 2 to T it is a 0 na, so that's why effective interval is only 0 to T by 2. And during this interval, what is the value? It is a 20 by T into T na, right? So it is a 20 by T into T bracket square into dt to the power 1 by 2. Please check square root of mean of squared value. We have squared here, but while finding the average value, whether we squared it, no, we have simply taken the instantaneous values. But while finding the RMS, we need to square it because it is square root of mean of squared value na. So now how to simplify it? We can write it as is equal to, yes, 20 square, that is a 400 divided by, let me take it as a T square. So it will be T cube into, this can be written as integration from 0 to T by 2 T square into dt na, to the power 1 by 2. I have taken 20 square, that is a 400 outside. T square, that is a T square, and this T, this will become T cube. Okay, so like this. So it is equal to 400 divided by T cube into T cube by 3. Limit is 0 to T by 2, no? Yes, to the power 1 by 2. So if we simplify it, we'll be getting it as 400 divided by T cube into, this is a T cube divided by 8 into 3, na? Right? T cube divided by 8 into 3 to the power 1 by 2. So it is equal to, we can write it as, yes, 400 by 8. Okay, so if you check, it is equal to 50. Okay, so yes. Let me write it as 400 divided by 24 into T cube into T cube here, right? So T cube cancel out. Okay, so it is equal to 400 divided by 24 to the power 1 by 2. Power 1 by 2, right? So, correct? What we have written? First of all, this function, and again we have squared it, right? We have squared it. So if you check, this will be equal to 400 by 24 under root answer. So it is 4.08 na, 4.08 ampere. This is the IRMS. Is this clear? Correct? Yes, yes, yes. So now this is the thing actually here, right? So this can be written as, okay, if we want to simplify this, then we can write it as like, yeah, this can be written as, suppose I am having the function like current I is here, this is a time t 0, right? So this, suppose this is t by 2, this is t, and again the same function repeats. And suppose this is a having the peak value of capital A, then we can write IRMS is equal to a square by 3. We can check it, a square by 3 into this is the function duration. Function duration divided by time period. To the power 1 by 2. In our case, A means what? It is a 10. Okay, in our case, A means what? It is a 10. Na? A means 10. So it is a, you can check 10 square divided by 3. Okay. So in our case, if you check, it is IRMS 10 square divided by 3 into what is the function duration? It is a t by 2. What is the time period t to the power 1 by 2 na? So you can check, it is equal to, yes, 10 square, that is 100 divided by that will be like a 6 na, 100 by 6, right, to the power 1 by 2. So again it is 100 by 6, again under root 2. So again you will be getting 4.08, right? So you can simplify in this way. Okay, miss, the thing is you can memorize this expression. Okay, this will reduce your solution time, right? That will help you. Okay. This is the one thing. And next one, they have asked for the average power loss. Yes, how to find the average power loss? We know now power loss means what? Current into voltage, current into voltage. So you can check here, from 0 to t by 2, current is non-zero, voltage is also non-zero, so product will be non-zero. During t by 2 to t, current is 0, voltage is non-zero, so product will be 0 na? So actual, the power loss is taking place only during 0 to t by 2, yes or no, right? So can I write average power loss? Average power loss, let me write average power loss. Average power loss, right? That is the P average, is equal to 1 by t integration from 0 to t. Okay, it is a V into I into dt. Average power loss means V into I means what? It is a power. I am integrating the power, right? Means I am adding the instantaneous values of the power over the interval 0 to t and again divided by t. So it is equal to what? We can write it as a, out of that 1 by t, yes, we can write it as integration from 0 to t by 2. During 0 to t by 2, what is V? It is a 0.1, sorry, 1 volt. 0 to t by 2, V is 1 volt, right? V is a 1 volt and current is the expression, right? So it is a 1 volt into, let me write the current expression. What is the current expression for during 0 to t by 2? That expression is 20 by t into t na, 20 by t into t. So let me write it as 20 by t into dt plus integration from t by 2 to t. What is the voltage? 0. Current is, you can check from if current, it may be anything na, 0 into that value will be 0 only, right? So this value will become 0. So we'll be getting it as equal to, yes, let me write it as a 1 by t integration over 0 to t by 2, and this expression is of current na, this expression is for current, so that will be your 20 into t by t into dt. So what it indicates? Integration of that current, right, divided by time. So that integration is nothing but area under the current na, this will indicates area under the current curve. Okay, so what is the area under the current curve? We can write it is equal to 1 by t into 1 by 2 into 10 into t by 2, right? So it is equal to 10, tt will get cancelled na, 10 by 4. So it is equal to 2.5 watt. This is equal, this is your P average. P average. Either you can simplify this, you will be getting the same answer, or you can take the integration of that current I is nothing but what? It is the area under the current I, na, right? So area of the current I we can find na, with this area under the triangle, correct? So for triangular wave, for the triangular wave, yes, we are having the function like, please keep it in mind. I average is equal to, we can find area divided by the periodic time, and for RMS value, we can write it as a this peak value square divided by 3 into function duration divided by time duration. Function duration means this is a function duration, and time duration means full time. Time duration means full time. Okay, so time duration means it is a 1 cycle time. Function duration means this is a function duration, right? So let me write here, this is a function duration And this full indicates the time duration, right? Let me write here. This is the time duration. Okay, yes. So we'll stop here. Now, if you are having any questions, you can ask. The forum is open to you. Yes, saying here, no? Current is zero. Current is zero. Okay. Current zero, voltage non-zero. Okay? No issue. Correct? Yeah. Yes, you can speak, Mahendra. If you are having doubts, please ask.
Sir, switching time is equal to TF plus TR, sir.
Switching time is TF plus TR. No, it is not like that. I will discuss it while discussing the numerical. Yet we have not discussed anything about the switching time, right?
Yes.
Actually, switching time means what? Suppose my switching frequency is 100 kilohertz. So it indicates in 1 second 100k times, right? My switches are turning on and turning off, right? Means one switch is turned on, after that it will be in the on state now for some time, and after that we will be having the next turn off transition period.
Okay,
So
sir.
it is not like the addition of the two simply, right?
Okay.
We'll discuss it in tomorrow's session. We are having the numericals related to the energy loss, na?
Oh, okay, sir.
At that time we'll discuss.
Hello, sir.
Yes.
Sir, that IRMS formula is applicable only for the triangular.
Just a minute. That IRMS formula, that shortcut formula.
Only for triangular waveform, or else anywhere we can apply.
No, this is only for triangular. We are going to discuss for triangular first. After that, I will discuss for rectangular, next quasi square wave. Okay. You will understand key for which waveform, which formula we need to put there, right?
Okay, sir.
This is only for triangular.
Okay, sir.
Yeah. Ramakrishna, you can unmute yourself.
Yeah, hello, good evening, sir.
Yeah, good evening.
So, sir, you have there were advantages and disadvantages of P, sir. You moved the slides so fast that we were not able to write, sir.
Okay. You want advantage, disadvantage? Yes, here it is advantage and disadvantage.
Yes, sir. So you moved the slides fast, so we were unable to write them. So
No, I will provide it. Don't worry, I will provide the class notes. After this session, I will be uploading it to the portal. Okay.
okay, sir.
From there you can download. Okay.
Yeah, okay.
Sir,
Yes, please.
sir, in the application of power electronics, we have discussed 3 points: active power compensation, reactive power compensation. Is there not applications?
Yes.
Sir, can you please tell some more about that? How, in what way we are using power electronics
No,
device?
actually, what we are doing, we are having one special area, that is the facts. You might have
Flexible AC.
studied facts, FACTS, right?
Flexible AC
transmission. Right. In that, whatever the devices we are having, the STATCOM and those things, right? Those will be applications of the power electronics only. Correct?
Okay, yes.
Okay. So
Sir,
here I only address that point, active and reactive, but actually you will understand it in the facts subject. Facts is a combination of your power system and the power electronics.
Okay.
Right? Okay.
Sir, and this active filter, sir.
Active filters are required in order to remove the harmonics. Okay.
Okay.
So there also we are using the power electronics technology. You will understand it while discussing the rectifier. Okay.
Sir, where do we use this active filter, sir? In power transmission, power systems.
In a power system.
Okay. Sir, one more. Sir, the last one we have calculated IRMS now, sir.
in the last here, na, just a minute.
Yeah.
Yes. Okay, this expression you are saying?
Yeah, sir, that's applicable. I mean, conditionally applicable or for any
No, this is only for triangular wave. Let me write here. This is only for triangular wave, huh? Not for other. Just a minute, my OneNote is not responding. I will close it and again I will reshare, right?
A square by
Just a minute. Okay. So this is only for triangular function. Okay. Is this clear?
yeah, clear, sir. Sir, yeah,
And the thing whatever we discussed here for average, na, area
Yes.
divided by time. This is for all the functions
yeah, yes,
because this is
and
a general expression, na.
yes.
Yes. Okay.
Sir, that power one also, sir. Please go to that
Which one?
power, sir. We have calculated power now. Last, just show it.
Last numerical, na.
Yes,
Okay. Here it is power.
just stay for 5 seconds.
Okay.
Yeah, thank you, sir.
Okay. Okay.
Hello, sir.
Yes, please.
Can you please explain once average current shortcut formula, sir?
Average current shortcut formula for the triangular wave.
Yes, sir.
Okay. I think here it is only average current you are saying.
Yes, sir.
It is simply the area under the curve, na.
Yes, sir.
Here we are having the standard formula. Average of any function is equal to 1 by its periodicity, integration over 0 to t, that function instantaneous values into dt. Simply look, suppose I am having the 10 numbers 1, 2, 3, 4 up to the 10. Okay.
Okay, sir.
So if I want to find the average value of those 10 numbers, how generally we find? We add the numbers, na, 1 plus 2 plus 3 up to the 10.
Yes,
And
sir.
again, we take the divided by the 10. The same way here we are doing. Actually, whatever the function y, that is the f of t we are having, it is a continuous function, na?
Yes, sir.
Right? So as this is the continuous function, so that's why whether it is having the finite samples, no, it will be having infinite samples. So is it possible to add infinite samples manually? No.
No,
So that's why we're integrating it. Integrating means we're adding it. Okay. And dividing with periodicity. So that's why this is the expression of the average. And the integration of any function over that periodicity, that will be your area, na? So that's why simply area divided by the periodicity will give you the average.
I'm asking shortcut formula. You said, sir, 1 by 2 into t by 2.
1 by t into area, na? This formula I have written here in the
problem.
shortcut. Yes,
In
just
first
a minute.
problem,
Area of
Ah.
I divided by t. This is the shortcut formula.
sir, 1 by 2, why, sir, here?
1 by 2 or 1 by t?
1 by 2 into t by 2. 1 by 2.
Okay. This 1 by 2 you are saying.
Ah,
Okay.
sir.
1 by 2 is the actually area of the triangle, na? This is a triangular.
Yes, sir.
What about the area of the triangle? 1 by 2 into this side, na?
Oh, okay, sir.
That's why I have written here 1 by 2. Clear?
Okay, sir.
Right? Okay.
Sir,
Yes.
sir, last doubt in the P average is equals to when we calculated the average loss.
Okay.
Specifically for this problem, can we do P average is equals to V average into I average for 0 to t by 2 period without the integration?
Yes, we can take that. I will discuss when we discuss the piecewise modeling of the devices, na? Whatever you are saying means when to use V into I average, when to use IRMS square into that register, like that will be that I will be addressing while discussing the piecewise modeling of the devices. Okay.
Okay.
Right
Sir.
now I have not addressed here because we have not covered that piecewise modeling, na?
Sir, in that diagram, 10 by t by 2 into 2 is means ISW formula, sir.
Where?
First problem.
First means
First
this
problem
one.
diagram.
This one, na?
Sir.
Ah.
Sir. I is equal to 10 by T by 2 into T means you said ISW formula, sir.
Yes, this is the I expression. Current I na. This is not ISW now. This is the I. So I have written the expression for the I here.
As same as ISW.
Yeah, it is same
Same
as with the
format, sir.
ISW.
Same
Right?
format.
Because it is a switch. They have shown the switch, na? Switch current. So ISW is there.
In same format, ISW format, you have write in here, sir.
Yes.
Yes. Okay, thank you.
This is a linearly increasing, na?
Yes,
So you
sir.
can write y is equal to mx. M is the slope and y is nothing but I here. In the previous case, we wrote it as in ISW form, right?
Into small t, why you are putting into small t, sir?
Actually, the thing is, we are having y is equal to mx expression, na?
Sir.
This y is nothing but y, on y-axis we are having the current, so that's why it is a current I. Instead of y, I will be there.
Yes, sir.
Now m means what? Slope, na? What is the slope? Slope is nothing but change in the y. You can check for this curve. What
10
is the
minus
change in the
b.
y? Change in the
10
y is
minus
10
b.
divided by change in the time is t by 2, na?
Yes, sir.
Into the x is there. X means what? T, na? So
Over.
that's why here t is there. That t is there, right?
Okay, thank you, sir.
Oh, yes.
Hello, sir.
Yes, please.
Yes, sir. I have doubt in thermal stability.
Thermal
Ideal
stability. Just a minute.
Yes, sir. I don't get that.
Okay. Yes.
Hello, sir.
Just a minute. I will address
Sir,
doubt here.
in the last question,
Just a minute. So one student is having the doubt in the thermal stability.
okay,
Let me address his doubt. Okay.
okay.
Yes, please. Thermal
Yes, sir. I
stability.
don't get this concept sir. For ideal case and this.
You don't get for ideal. For ideal case, it is unbound. Because for the ideal switch, we don't have the limit for the voltage rating and the current rating. Na?
Yes, sir.
We wrote during on state, the current is changing from minus infinity to plus infinity. It is allowed, na?
Yes,
For
sir.
ideal case, it is from unbounded, and the ideal case we don't have the power loss also.
Yes, sir.
So if we don't have power loss in the ideal case, then whether there will be the thermal constraint in the ideal case? No.
No, sir. No.
So thermal constraint is not there. Voltage and current are also infinite, na? So that's
Yes,
why it will be unbounded area for the in the case of ideal. So that's why
So-
you check in the ideal case we have shown this full plane, na? In the ideal case we have shown this one. Just a minute. I think its percentage is very high. Just a minute. I'm sharing a screen. Please wait.
Yes, sir.
Okay.
Yes, this is the safer operating area for the ideal case, right?
Yes, sir.
This is the entire VI plane, correct?
Okay, sir.
And in the case of practical switch, we are having the limits, na? What limits we are having? The switch voltage or the switch voltage blocking capacity.
Yes, sir.
It is a finite. So now that's why here we have represented here plus V dash and minus V double dash. The same thing we have written. When switch is in an off state, it can block the voltage. That is a minus V double dash to plus V dash I have shown here. You can check. Yes, minus V dash double dash to V dash. So that's why
Yes,
these
sir.
are the limits. Okay, so that's why we have taken the points like V dash and minus V double dash. Similarly, for the current also we are having the limits, finite currents, right? I dash and minus I double dash.
So,
Next,
sir,
from
which
that,
means,
we have drawn this rectangular area. Okay,
sir.
but again
for-
in the practical case, when we are operating the point, when we are operating the switch at these points, as at the near to the corners, okay, so it will be like the voltage is maximum, current is also maximum.
Yes,
So
sir.
it will cause a high power loss again, because power loss is nothing but what? Voltage across the switch into current flowing through the switch.
Yes,
So
sir.
due to that high power loss, the device may get damaged. So that's why the manufacturer suggests us that instead of operating the switch, okay, under this entire rectangular portion, it gives, okay, he will give us the limits, like means some margin will be there, okay. So
Okay.
he will suggest that instead of that V dash, go for this somewhat lesser value. Instead of this minus V double dash, go for this somewhat lesser value. And accordingly, we have drawn that inner dotted rectangle is there, right?
Yes, sir.
Okay, and after that, I have shown, because only voltage and current is not the constant now. We are having
Yes,
the
sir.
thermal constant also.
Yes,
So
sir.
that's why these cross lines, these indicates the thermal constants. That is the power limit.
So here the thermal constraint depends on the actual voltage and current value. Right, sir?
What? Will you please speak a louder bit?
Oh, so here the thermal constraint value or the temperature value depends on the voltage and current values, right, sir?
Yes, depends on voltage and current, right?
Okay, sir. And for
Voltage
ideal
across
case,
switch
the
and current
temperature.
going to the switch.
Okay, sir. And for ideal case, can the temperature reach any value, sir?
For ideal switch, yeah, for ideal switch, there is no issue of increase in temperature, na, because power losses are zero,
Okay, sir.
right? Because
Yes,
your heat will be generated when the power loss will be taking place, correct?
Yes, sir.
Yes, yes.
Okay,
Sir?
fine.
Yes, please.
Sir, once you could explain IRMS value formula, sir.
IRMS in numerical one.
Yes, sir.
Okay. IRMS means whether whatever we have calculated with the expression or that final shortcut.
Triangle formula, sir. How here how we get sir 3, sir? A square by 3.
A square by 3. Simply what the thing, you can rearrange this term 400 by 24. How it will be, you can check here. I can rearrange it as like 10 square, okay, divided by 3 into here it is we are having a T by 2, na, right?
Okay, sir.
And it is a T, and this is a power 1 by 2. You can check here. Simply think what I have done. I have taken this as a function time, this as our total time, okay. So it is like it was a 400 by 24, so it will be like 100 divided by what? It will be like 6, na. So here 3 into 2 will be 6 here, correct?
So on upper calculation, you did this equation, sir.
Upper calculation I did directly, matlab with the equation. And last one, whatever I have written, this is the shortcut method.
Okay.
Simple thing is what you do, instead of considering this as a 10, na, instead of considering this as a 10, consider it as a consider it as a right? Write the expression for this curve by considering this as a. What is the expression if I consider this as a? The expression will be like I is equal to, yes, you can check, A divided by T by 2 into T, na?
Yes, sir.
So it is 2A by T into T. So after this, you can take the RMS value of this function. Okay. So you will be getting this expression here. Whatever we have written, this expression you will be getting.
Okay, sir.
Right?
Sir, and power
Yeah.
loss also, sir.
In the power loss, yes. What is the doubt?
Second step, sir.
This one?
Yes, sir.
Okay.
How
What
we
we are
got V0, sir?
Yes, please. Will you repeat?
V is equal to 0 is constant, sir. How we get that, sir?
Okay, this one, na?
Yes, sir.
V is non-zero. Sorry, V is non-zero. Current is 0 actually. I will tell you. 0 to T, I have taken the interval.
Yes, sir.
That is again divided into 2 sub intervals, 0 to T by 2, T by 2 to T. Right?
Yes.
So T by 2 to T, you can check V and I values. From T by 2 to T, T by 2 to T, current is 0, na?
Yes, sir.
Voltage is a non-zero. So if I take the product 0 into V, that will be 0, na? 0 into V.
Okay, sir.
Actually, initially I wrote that voltage is 0 and current non-zero, but it is not like that. Yeah, from the waveform, you will understand that the voltage, that current is zero, voltage is non-zero, right? Anyways, the product of zero, one is zero and second is a non-zero value, that will be zero only, right?
Okay, sir.
Okay, okay. Next,
Hello, sir.
yes, please.
Sir, in the last question, the function duration, if there is a square wave, then the function duration will be 0 to t only.
No. For square wave, yet I have not discussed, right? Tomorrow we'll discuss about the square wave. Don't get
Sir.
confused now. This is only for triangular wave.
No, sir, I am not discussing about the formula. If we apply IRMS, that integration formula, then in that duration will be 0 to t only, right? Because
It depends. It depends. Suppose if you are having the rectangular, you are saying rectangular, na?
yes, sir, square.
Square wave, na?
Yes, sir.
Suppose you are having the function like this. Let me write a square or rectangular. Okay. Square. If we are having the function like this, t0. Suppose this is the. Let me write it as a y. Suppose this is t by 2, and here it is a t, and this is like this. Okay.
Okay, negative value. We are only considering DC
If the
value.
negative value is there, then the formula will be changing. Okay. Then in that case, the function will be like here. Both will be t and t, means t by 2 and t by 2.
Yes, sir.
Yeah,
So
that will
in
change.
triangular wave, we have considered t by 2 as function duration because at t by 2 it becomes 0. I becomes 0. That's why we have taken
Yes,
function
yes.
duration.
Correct.
Okay. And in thermal thermal constraints, sir.
Yes.
So why the value of the magnitude value is different there, minus v dash and plus v dash, and why it is different value magnitude?
No, this is only simple one generalized statement I have done.
Okay.
It is not like that both will be both will be like different values, and it is
It
not
can-
like that both will be same values for all these
Acha,
features.
it
is
can
not
be
like that.
anything.
Anything,
It can be-
anything.
Okay. Okay.
Yes.
Thank you.
Okay.
Thank you.
Hi, yes, please.
Hello.
Yes, please. You are audible.
So can you go through the switching constants of switching?
Can you?
Switching transient waveform.
Switching transient waveform. Just
during the turn on, during the turn off.
transition behavior. You mean to say
Yes, yes.
this one?
Sir.
Okay, huh?
The linear waveform, how you what portion?
Will you please speak a louder bit?
How that linear portion of the waveform follows in
Linear and why the linear we have taken? Okay.
why not the any other waveform?
Yes.
Why not the any other wave? Why follows only linear?
You are not actually audible clearly. Please speak louder.
Why
Or you can post it in a chat box. Okay. I will check. Yes, Siva, na?
Yes, sir.
Yes. Will you please speak louder? Or are you putting it in chat box?
Just now I put in the chat box.
Chat box, na? Just a minute.
My question is why that the linear portion follows linear fashion. Why not any other?
Okay. Why the linear and why not the other? Okay.
Why not the
No,
other?
this is the only for initial discussion I have taken, because the thing is we know during the turn on transition, okay, current will increase and voltage will decrease. So that's why I have taken it as a linear. But in the numericals, when we discuss, okay, they in the numericals you will understand where we will be having the number of different combinations. Okay.
That depends upon the different type of.
It depends on
different type of switch. the current.
Yeah, it depends on the switch. Actually, the thing is, we are modeling the switches in the three ways. One is like a constant voltage source during the constant voltage source during the on state. Second one is like R and voltage source, and third one is like only resistance. So it will change accordingly. Okay, it depends on the it will vary switch to switch. This is for generalized case I have considered.
Generalized, just solving
Yes,
purpose.
generalized. It is not like a thumb rule is like this. No, it is not like that.
Okay.
Right? Okay.
Hello, sir.
Yes, please.
Sir, what are the electromechanical converters, sir?
What
We
are
have
the-
discussed electromechanical converters. Sir, you have discussed at starting, sir. What are electromechanical
Okay,
converters?
the advantages and disadvantages. Here,
Yes. Yes, sir. Yes, sir.
electromechanical converters means what? It is general statement I am doing that. Suppose I am having the rectifier. Okay. What our rectifier is doing, it is giving the output in the form of DC, right? So, in the mechanical system, we will be having, okay, the like a generator, we will be having the generator, DC generator.
Yes, sir.
That will be giving the output, okay, as a DC. So I am
Yes, sir.
comparing I am simply comparing the DC generator and the rectifier.
Okay, sir.
Right? So electromechanical converter, it depends or it changes accordingly your power electronic converter. If power electronic converter is rectifier, then your electromechanical converter is like a generator, right?
Okay, sir.
Like this. Okay.
Sir, one more doubt, sir.
Yes, please.
In practical switch, why are you using external circuit requirements, sir? Why not
that you will understand when we study that practical switch. You can check SCR. You might be familiar with the SCR, right? In the SCR, we require the gate cathode circuitry, na? Yes or no? In order to circulate the gate current, in order to provide the gate pulse, we require a gate cathode circuit.
Yes, sir.
That is nothing but your external circuitry. Also, you can check the BJT. In the BJT, we need to connect the elements across the base and that collector emitter terminal, right?
Yes,
BJT is a current controller, na? Right? So that is nothing but your external circuitry. Okay.
Okay, sir.
But in ideal case, because the switch is ideal, na, we are assuming that there is no practical circuit or the external circuit requirement. Okay.
We are considering, sir.
Yeah, we are considering because we don't have the ideal things in the real life, na. Our main motto is to design the switch which should not require that external circuit. But whether it is possible?
No, sir.
No, that is the practical difficulty.
Okay, sir.
Right? Yes. Yes, sir. 7 students who raised their hand. Yes, I have allowed. Please.
Sir, hello, sir.
Yes, one by one, please.
Hello, sir.
Yes, Avinash, you can speak. Just a minute.
Sir, in this characteristics, sir, power limit is this crossed, sir. Means the inclined line is
Here.
Yes, sir.
So you mean to say that the thing is, if my operating point is here. Okay, power limit is not crossed at this operating point. The voltage and current limit is crossed, but this is just a bit, na?
Yes, sir.
That can be acceptable. Right?
Okay, sir.
Right? Okay. Yes, next one is.
Sir, in RMS value of Y, you have written formula, no, sir. Can you once show?
Just a minute. Which formula?
Here only, sir. Sir, down, sir.
This one.
This one. Sir, here square root and square will cancel. Then it will be equal to RMS equal to average value of f of t, no, sir.
No, square root and square it will not directly cancel. It is the average of that squared value, na? It is not like this. Average
of that function square.
Average f of t and its square. Suppose if this is the case, to the power 1/2, then it will cancel, no doubt. But this will not cancel, na?
Okay, sir.
Right?
Sir, again.
Because it is average of the squared function.
Okay, sir. Understood.
Right? Okay. Yeah.
Sir, again, one more, sir. What is the difference between thermal stability and constraint, sir? Thermal constraint.
Thermal constraint and thermal stability means thermal constraint decides whether your switch is thermally stable or not. Because the thing is, in our practical switches, what is happening when the power loss is taking place, then the heat is generating. Due to the heat generation, the device temperature is increasing. Device temperature is increasing means it is associated with your thermal stability. Okay. So actually what the manufacturer does, the manufacturer generally gives one average power limit. Okay. Means if the device is having the average power limit above that of whatever the mentioned by the manufacturer, okay, our device will get damaged. So that's why we need to put it till the limit only. Constraint means it is like a limit.
Okay. Stability
and if we operate the device, if we operate the device below to that constraint, okay, below to that limit, then it is like our device will be in the stable mode.
Okay, sir.
Right? Yeah.
Thank you, sir.
Yeah. Yes, please, Vishwanath.
Hello, sir.
Hi,
Am I audible, sir?
Yes, please. You are audible.
Sir, in the practical case, why are we taking the limits for voltage and current?
In the practical case, why we are taking the limit for
voltage and current values?
Okay. Voltage and current, because in the practical case for our switches, we are having the limit for average power loss. We cannot allow our switches to go beyond that limit. The thing is, if the switches are operating beyond that limit, okay, then the heat generation will be, power loss will be more. Due to that, more heat will be generated, and due to the more heat generation, our device will get destroyed or get damaged permanently. So that's why in practical case we are having the limits. But whereas in the ideal case, if you check, as we don't have in the ideal case we don't have a power loss. So as the power loss is not there, so there is no issue of increase in the temperature, heat generation, right? Heat generation will not be there, so temperature will not increase. So that's why device will be thermally stable only. Is this clear?
Sir, you are saying that to arrange the certain limits to the switch, so that's why we are taking the limits.
Yes.
Certain ratings of the switch depends upon the limit.
Yeah, it depends on the rating of the switch actually, and the rating of the switch depends on if you want to change the voltage rating of the switch, again it is related to that your doping density. Whatever I addressed at the starting, doping density is inversely proportional to your breakdown voltage or the blocking voltage capacity. Means it depends on the device actually construction itself.
Okay, sir.
Right? Yeah.
Sir, and one more thing, are there any other constraints other than the thermal stability to determine the safe operating of the switch?
No, that voltage and current and the thermal stability, that's it.
These three only determines if the switch is very safe to operate or not.
Yes. These three are the constraints.
Yeah, okay, sir.
Right. Okay. Yes, next.
Hello, sir.
Yes, please.
Sir, in the thermal stability SOA of practical switch net, I didn't get how that power limit curve came over that slanting line.
This one?
Yeah, at the corner we drew a line connecting the diagonal side, power limit line.
Okay. Actually, the thing is, this is like a power limit. Okay. So power limit means what? P is equal to VSW into ISW. Okay. The thing is, if I operate the switch at this point, corresponding to this point, the current is high, voltage is also at the upper limit,
Yes.
So manufacturer says that if you operate the switch at this point, then it will cause the high heat generation, and there is a possibility that device may get damaged. So due to that, the manufacturer actually advised the engineers or whoever who is using the switch, okay, that don't go for the upper limits, simply below to that the upper limit, okay, near to the upper limit you can operate the switch.
Okay.
Right, and like this we are having these constraints.
Good.
This now in this case, if you check, this should not be my operating point for my switch. if I operate the switch at this point, our device may get damaged. I'm saying may get damaged. Okay.
Okay, sir. Yes, sir. Got it. Sir, one more thing that we mentioned about high power application, medium power application, like on what basis are we at the
It
introduction?
depends on a high power and low power, because in a power system, HVDC transmission is there, na?
Yes, sir.
So for that, as the name suggests, it is HVDC, high voltage, na? So it depends on the application for which the application's voltage and current rating. It depends.
Okay,
Generally,
sir.
for the traction system, it comes under the medium power.
Sir,
Because comparatively, the required motor rating and those things, okay, those are moderate, medium.
Sir, what about our renewable solar case?
Renewable is also comes under the your medium power or high power. It depends, right? Means suppose if I am using the solar plant, okay. Now that on that solar plant voltage and current capacity, it depends whether it is a high power or low power, or the high power or low power application. Because ultimately, why I have not mentioned there, because it depends on that particular plant.
Okay, okay,
Right?
sir.
Okay.
Yes, sir. Yes, sir. Got it, sir. Thank you.
Okay. Yes. Anyone else?
हेलो
हाँ, yes, please, Abdul.
हाँ सर, आप VSW ISW वेवफॉर्म है ना सर?
Just a minute.
जो
where is that?
प्रैक्टिकल स्विच के बाद,
प्रैक्टिकल स्विच के बाद ये ट्रांजिशन बिहेवियर.
हाँ ये है सर. मैं क्या बोल रहा हूँ, ISW है ना सर?
हाँ.
ISW का स्टार्टिंग, आई एम सॉरी, ये TF है ना सर? ये TF का 0 पॉइंट से मैं आपको स्क्वेयर वेव या साइनसॉइडल में ऐसा इंक्रीज होना चाहता हूँ मैं. ठीक है, तो अपन का क्या होना, या एक इंक्रीज होना उसके बाद कांस्टेंट होना है, राइट सर? आउटपुट सब मैग्नीट्यूड मेंटेन करना है.
ओके.
नहीं, मैं क्या बोल रहा हूँ सर, TF जो इनिशियल पॉइंट से, TF जो इनिशियल वो पॉइंट से मैं आपको ये फाइनल पॉइंट से मैं क्या बोल रहा हूँ, मैं स्क्वेयर वेव जैसा मैं रिप्रेजेंट करना चाहता हूँ.
लेकिन कैसा है कि एक कैसे रिप्रेजेंट करना ये हमारे हाथ में नहीं है. इट डिपेंड्स ऑन
आप जी मैं क्या
डिवाइस प्रॉपर्टी.
सर आप कैसा करेगा, तो जो कैपेसिटर चार्ज होता ना सर लीनियरली, वैसा रिप्रेजेंट करे आप.
No, I have taken generalized plot here. I have taken generalized plot because my idea is what, when the switch is switching from on to the off state, the voltage is increasing and current is decreasing. So simply I have taken it as a linear. That is a generalized way. And whatever you are saying, okay, because it depends on it is not in our hand, na. It depends on that device property. After that, if you check, I am having some of the numericals where you will understand. Just a minute, I will show you. Yeah, in some of the cases they have given this plot. This is GATE 2005 question. They have given this voltage and current plot. Now you can check here. They have given linearly decreasing and here it is linearly increasing. So most of the cases the thing is like this. So that's why we have taken generalized way. Or you can check our booklet also.
It is
decreasing, increasing they have given. And in the second switching scheme, na, tomorrow we are going to discuss this question actually.
ठीक है sir.
Here it is a constant and here it is a decreasing like this. Means I am not claiming that ki just a minute, where it is. Yeah, I am not claiming that it will be like a thumb rule that it will be like this only during the on and during the off. No, right?
जी.
It depends on the device property, right?
अच्छा सर, और एक सर एक नॉर्मल जनरल है सर. सर अपन जो ये पोर्टल में टेस्ट्स कंडक्ट करते हैं ना सर, टेस्ट फॉर एग्जाम्पल कौन सा भी सब्जेक्ट हो टेस्टर रहते हैं ना सर.
यस यस.
हाँ, वो जो अपन कंडक्ट करते समय जो अपन लिखते से टाइम पे थोड़ा आंसर्स गलत है सर. क्या है का तो कुछ मिसकैलकुलेशंस हो, एरर्स है हो, कौन सा भी थोड़ा गलत है.
मतलब
जी वो
यू आर सेइंग और क्वेश्चन डेटा.
नहीं सर, वो क्वेश्चन डेटा थोड़े क्वेश्चन से प्रॉपर है, प्रॉपर क्वेश्चन है उसका रिलेटेड. फॉर एग्जांपल मैं रॉन्ग किया समझ लो सर, उसका जो एक्सप्लेनेशन ठीक है, हाँ ये स्टेप बाय स्टेप करना को है
Okay.
थोड़े क्वेश्चन का कैसा है का तो उसका एक्सप्लेनेशन बहुत अलग है का तो उसका मतलब क्या है का तो
Okay,
फॉर
means it
एग्जांपल
is
आप
not related, you are saying.
हाँ राइट
Just a minute. I will note it, and I need to actually yes, address this issue to the higher authorities. Just a minute. Means you are saying that proper explanation is not there.
हाँ नहीं है सर मैं 2 या 3 सब्जेक्ट का टेस्ट में लिखा सर उसमें यही इश्यू था क्या मेरा पॉइंट ऑफ व्यू थोड़ा गलत है नहीं का तो उन लोग ज्यादा एनालिसिस करके करे नहीं मालूम हो रहा मेरे को
Okay.
जी वही है साहब दूसरी बात नहीं है
ठीक है. I will check.
हाँ सर और एक आखिरी बात है सर ये
Yes, ना?
जी
Okay.
सर और एक बात है सर आपका जो अभी ऑनलाइन क्लास चल रहा था ना
हाँ
अभी आपका वॉइस आ जाता है फ्लुएंसी क्लियर में आ जाता है लेकिन आपका वीडियो बहुत देरी से हो रहा तो एक्शन इज नॉट प्रॉपर विद द साउंड
Okay. That might be
आप
due to the streaming issue. I don't know.
अच्छा मैं शुरू से देख रहा था आपका क्लास है हाँ इसलिए थोड़ा वही सर वो उतनी है सर ओके थैंक यू सर
Okay. Yeah.
सर और एक आखिरी बात ये नोट्स का कब मिलेगा सर पीडीएफ
अभी just after this session I will be uploading it. Okay.
सर आपके तरफ से नहीं का तो फिर भी आपका टीम बैक एंड टीम उन लोग
नहीं
का
मेरे
हमको-
तरफ से मैंने उनको बोला है ये पूरा राइट उन्होंने मुझे दिया है. Right?
अच्छा ओके
I will
थैंक यू सर
upload.
थैंक यू फॉर योर सपोर्ट
Yes. Next. Pratyusha, are you there? You have raised the hand. Yes, please. Hello. Do you have any doubt?
Sir,
Yes, please. You are not audible. Will you please speak louder?
sir, is my voice audible?
Yes, you are audible. You are audible. Please go ahead. Hello. Next one is there, I think, Moka. You have raised the hand. Do you have any question? Yes, Pratyusha, you can ask the question. Okay. I think all the doubts are resolved. You are not audible. Pratyusha, you can speak. Hello. Okay. Haripriya. It is showing that your mic is it is showing that you are speaking, but you are not audible here. That is the problem. Yes, Haripriya, do you have any doubt?
Sir, am I audible?
Yes, you are audible now. Please.
Still, there is audio problem, sir.
Okay, no issue.
Sir, in numerical problem, is there any shortcut for average power loss?
Average power loss, yeah, for that, yes, we are having the shortcut. Regarding the average power loss, the only thing is we have discussed this one here till now, this numerical only, okay? Tomorrow when we discuss the numericals remaining, at that time you will understand. The average power loss shortcut means what? Power loss is nothing but the product of the two, na?
Yes,
Voltage
sir.
and current.
Yes, sir.
So in order to find the average power loss, suppose here during 0 to t/2, this is a constant na voltage.
Yes, sir.
So I can take it outside of the integration. So only thing is I need to integrate this term, and integration of this term is nothing but the area.
Yes,
This
sir.
type of shortcuts actually we need to understand, right?
Yes, sir.
Hello, sir.
Yes, please.
Sir, how voltage increases during off state in turn of transition, sir?
How voltage increases?
Increases during off state in turn of transition. Means how it happens.
During turn of transition. Okay.
Yeah,
Okay.
yes, sir.
Now actually thing is, initially when switch is in on state, the voltage will be 0. And when we say that when we say that the switch has successfully turned off, when the switch is able to block that voltage, na, right? So this characteristic, na, voltage is increasing, current is decreasing, that you will understand while discussing that particular switch characteristic.
Okay, sir.
Right?
Hmm.
In the SCR, we are having the dynamic characteristics of the SCR. At that time, you will understand.
And at the same time, current also decreases now, sir, during off
Current
state.
also decreases. Current also decreases.
On what basis we can say that, sir?
Actually, it depends on device operation. Yeah, this is our actually general discussion. It varies device to device.
Okay, sir.
Right?
Hmm.
Okay.
Thank you, sir.
Okay. Okay, right. Thank you. Thanks to all of you. Pranav, do you have any doubt?
सर आप नोट्स एक्स्ट्रा देने वाले हैं क्या? ये अभी जो आपने राइट किया था उसके अलावा देने वाले हैं क्या?
नहीं, यही देने वाला हूँ मैं.
ओके सर, ओके.
राइट? ओके.